Thanks, everybody. Starting day 2. Day 1 was awesome, and lots of different things happened, but glad to be here. We have a bunch of people online as well. You guys are going to remind me to not be muted when we restart, right? You're going to be like, don't forget to unmute, because I did that twice yesterday. Today, we're going to start with data science program overview, and then we'll have 2 of the upper div advanced classes. It's very different from yesterday, but still really engaging. So data 102, machine learning class, and data 100, the advanced data science class. How do you like summarize what data 100 is?
The junior level data science.
The junior level data science class where you learn all the tools. So without further ado, I'm going to bring John DeNero up here, who is our associate dean and overseeing this crazy transition to a new configuration of our program.
Hello again. And I think this morning, or maybe this afternoon, you also get to hear about Data 104, which is the Human Context and Ethics Upper Division course. So so you get a nice tour of the other courses that are at a more advanced level. And I figured I'd just give you a quick overview because I got some questions yesterday about like what the program looks like and that kind of thing. So if you have any questions about how it's scaling and what exists at Berkeley or elsewhere, I'm happy to talk about that. Data 8 was the first data science course. It now has a couple of courses that lead into it. Data 6 you heard about yesterday afternoon, and Data 4, Data and Justice, is really an early introduction to a variety of topics, including human context and ethics. But the important thing is that both of these are designed to bring in populations of students that might not otherwise take Data 8. And I think it's really important for the expansion of the field. There are a variety of lower division courses that we've developed. So this means there's taking in their freshman or sophomore year typically that extend Data 8, but aren't they don't have a lot of prerequisites. In fact, they often are fulfilling prerequisites. So there's a probability course that often students take at the same time they're taking Data 8 in order to see more of the mathematics behind the statistical inference, because some students really crave that. They think, oh, this like simulation stuff is really nice, but how do I, prove that it's working or see what the general formulas are? And that's it's something that a lot of students want. And so we have a probability course for that. The computational structures course is very similar to a traditional programming or introductory computer science course, but it has some data science examples woven in. You implement a table data structure there, so you kind of see a connection to Data 8. But we really do have some courses that are designed to support students going on into a minor or a major. There's the economic models course that Eric teaches. Then there's just a variety of other courses across campus. They're not all labeled data science courses, but a lot of them do leverage what students have learned in Data 8. Then we transition into the upper division. There are 3 kind of core courses that a lot of our students take. Data 100 is the largest upper division course on campus. It carries forward a lot of the themes from Data 8. Except for now, students have taken linear algebra, they've taken programming, they've often taken probability, and so they're in a good position to kind of make a second pass at higher scale, more variables, and more sophisticated techniques. The probability for data science course includes all the topics of our traditional upper division probability course, and a few more, I think, and also asks students to run simulation of those probability models using computation in order to gain kind of intuition about what's going on. And so it's like a really nice way of leveraging the curriculum to teach an old topic in a new way. And the human context and ethics course is really trying to draw students into the important reflection of what the impacts are of all this technology and data science. Then we have a bunch of electives that are popping up in the upper division. So advanced courses, you'll hear about the data inference and decisions course next. There's a new data engineering course that talks about not only SQL-based database management systems, but all the variety of other ways of capturing data and storing it and managing it that have popped up in the world. And a variety more. So I'll let you read the titles and see if anybody has questions about any of these courses in particular. But basically, you know, if you're teaching data aid, particularly at a community college for someone who transfers into Berkeley, this is the kind of curriculum that they're headed toward. Huh?
Maybe supplemental classes that you could potentially teach.
Yes, definitely. I think that the probability course and the computational structures course are great targets for teaching at a community college. They're both lower division. They're called Data 88S and 88C, S for statistics, C for computing. And we'd love to talk about potentially offering them because I think it would be a really good fit.
The courses like Data 8100 are fairly well defined and organized and freely available on the web. Or are any of these other courses similarly structured where if somebody wants to join a topic curriculum like that, they could go and have a great starting point that they can do Data 8?
Yes, a few of them. This probability for data science course is Data 140, has an open textbook, open materials, kind of structured just like Data 8 and Data 100 in terms of providing everything that you might need to run the course. That's the one I know about. It might be that we'll find out when Ramesh comes and talks about Data 102 that that's all open as well, but I'm not sure. So you could ask him.
My course is in the same cookie cutter, but nobody's asked to borrow it yet.
So that's the economic models course, ready to be taught everywhere.
Open textbook.
Now a good time to ask questions about any of the courses.
Sure.
So can you do a quick compare and contrast between the computational structure, data science, and computer science?
Yeah, great question. So how do you compare computational structures and data science to what we have as our typical first course in computer science, which is the structure and interpretation of computer programs? I would describe them as extremely similar. They even share some projects and homework assignments and problems. This data science version is a 3-unit course instead of a 4-unit course. So basically what we've done is cut out the last unit, which is about how to build an interpreter from the programming structures course that we already had, and took the rest of the content, spread it out over a semester, and then swapped out some of the examples to connect with data science. But actually there wasn't a whole lot of swapping. One thing that did happen is that the older version of our core computer science course had kind of a data science project in it. This was before Data 8 existed. There was like a download some Yelp data and put it on a map and do some predictions with it kind of project, because there wasn't a data science course. But then when we created a data science course, we took that out of the computer science core and replaced it with something that was kind of more central to computer science, got some recursion in it. So that project actually moved to the data science version of the course, the computational structures in data science. So yeah, I think the themes in computational structures and data science would be very similar to what anybody would expect when teaching an intro programming course.
Like OLM notation or abstract data.
Yeah, good question. So what about complexity? It is in there in terms of the definitions and some simple examples, but the deeper treatment of complexity and algorithm studies is in the second course in computer science. And that is, required for the data science major. So the students who kind of continue on in this long enough will see all that, but it's not in the first course. I mean, it's a little bit in the first course.
So when you say required for data, so this is not the entire.
This is not the data science major. This is all the data science courses. I'll show you the data science major, I think 2 slides from now, if you want to see that. But the data science major does have some requirements outside of data science courses, like, math courses and things like that.
Talk a bit about the
perspectives for data engineering. Look kind of that first row, data inference and decisions, statistical methods for data science, data engineering, data mining analytics.
Yeah, great question. So all of these kind of in the electives row, upper division electives row at the top have different learning goals depending on, where they sort of fit in the prerequisite chain. I'll point out two in particular. The data inference and decisions course is really meant to be taken after data 100 and after probability in order to show you applications of decision making and machine learning and probability that are kind of more advanced, as some reinforcement learning and stuff like that. And the idea there is to set people up for either continuing on in research or like handling more technical problems that are atypical, like making multiple hypothesis tests in series and trying to understand what to do with that. The data engineering course, I would say, also is meant to follow data 100, which has a database component to it. But here, the data engineering course covers a lot more about databases. So you finish learning all the details of SQL, and then you understand how databases actually process queries. And yeah, so I'd say these are just two different possible extensions from data 100.
Probability for data science, and statistical methods for data science. Distinguish.
Yeah, great question. So there's three things that say either probability or statistics. And what are the different topics in them? The level of maturity goes up as you go up the slide. So probability and mathematical statistics for data science is a lower division course. It does not expect that students have taken linear algebra already. It really is very much focused on the techniques that are taught in data 8 and what's the math behind them. The probability for data science course is kind of everything that an undergraduate should know about probability. So that does include linear algebra and writing, talking about multivariate Gaussians and things like that. And then the statistical methods for data science course, there's a lot that still hasn't been covered when you make it through data 100. They don't know anything about time series. They don't know anything about, they know quite a bit about interpretation of linear models, but certainly not everything that you would want to know. And so kind of using statistics to understand the world still has some topics that were left out of the core data science curriculum. And this is really meant to fill those gaps. And so if a student's taken this, then they're actually ready to go take any special topics course within the statistics department is the idea behind the statistical models for data science course.
So you heard the linear algebra for data science, is that offered by that department?
That is offered by math. So math decided to offer a new version of their linear algebra course just recently developed that was meant to support all the data science and computer science students with a kind of machine learning bent and the statistics students who are kind of flowing through these courses.
Right, so those students don't take traditional linear algebra.
Yeah, I don't know the course that details that well, but I don't think it's that different, except for that our linear algebra course on campus previously included differential equations and was very much focused on supporting engineering and chemistry and physics. And so they thought swapping a few topics out, making sure they got through singular value decomposition in the first semester, and that meant not including differential equations was kind of part of the change. Okay.
Well, the last remaining course that they're called is data mining and analytics. Talk a little bit about that course.
Oh yeah, the data mining and analytics course, very popular course. We often get 500 people in it when it's offered.
We should have him come to the workshop.
Yeah, we should really get Zach Pardos, who teaches it, come to the workshop and talk about it. But there's a lot of applied machine learning where a lot of the story is how do you collect and represent the data that you're going to apply some machine learning method to.
Would you describe the difference between the data? One or two sentences.
What's the difference between the data inference and decisions and data mining and analytics? I think it's just a different set of topics. The data inference and decisions topic list includes things like reinforcement learning, understanding like multi-arm bandit problems, multiple hypothesis testing I mentioned.
And that's the next speaker.
And I think a lot of that is just not in the data mining and analytics course, which is much more about like, supervised learning and how to actually use it in the world. Okay, this is fun. There's even more. There's like a non-technical kind of vocational stuff. There's an honors seminar where students do independent projects based on research. There's a career accelerator. There's a teaching internship for students who want to get involved in teaching. And those are all the courses we have, which is, not actually as many as in other departments like statistics or something like that. But it's getting to be a longer list. The total enrollments is going up. Before 2020, these numbers don't really make any sense because we had data science courses, but they were labeled as statistics or computer science courses. And so actually a lot of this growth here in computer science, which I showed for reference, is actually just data science courses, data 8 and data 100. And then they got reclassified as data science courses, which is what they are. And so then they ended up in this bucket instead of this bucket. But if you kind of look at everything that happened from 2020 onward, we're still seeing quite a bit of growth in the data science course enrollments overall. And so now we're kind of at where computer science was 10 years ago in terms of the total enrollments, but it's concentrated into a smaller number of courses. And we'll see how much it continues to grow. Hopefully we'll be able to add more courses.
One of the things when you first asked about when we talk about data science programs is, are you bringing net new students or are you just pulling them to the science? How do you think about that or look at that?
Yeah, good question. So we're pulling from computer science or bringing in net new students. The population of students that major in data science and take data science courses is pretty different from the computer science students. There's some overlap, of course. But we're pulling in a lot of students who become double majors with economics, with business, with biology, with some of the natural sciences. So we are definitely kind of adding computing and statistics to students who might otherwise not take so much of that. And there's definitely some pull from computer science, which I think is natural. There's some students who get excited about computer science because they want to build applications, and so they study computer science, but there's some that want to understand the world and use like applied machine learning to learn stuff about data analysis, and so they end up in data science instead. It's totally fine. The place where we have seen a reduction is in the size of the statistics major, which dropped from 250 a year to 150 a year. I think it's probably going to grow again, but we have seen a dip as like everybody got excited about data science at once. Quick overview of the degree program. So here's what it means to major in data science at Berkeley. You take data 8, you take programming, you take a second programming course that's about data structures and algorithms. So this is only offered in computer science, not something that has a data label. Even though it's called data structures. You take 2 semesters of calculus and a semester of linear algebra. That's the lower division requirements. And then you take the upper division, which has data 100 you'll hear about, human context and ethics. Upper division course you'll hear about, the probability theory course I mentioned. This is the data 102 course that you'll hear about. And then you have to take some electives. And most importantly, you have to take 3 courses in some domain area. Where you're learning you're learning about the data. So not just generic data processing, but also you have to go deep into some domain where people actually use data to make decisions or learn about the world. So there's been some growth in the number of degrees earned. Here's just a quick overview of the domain emphases. Can't possibly read them all, but I'll just stop talking for a second and let you take a look. Each one of these has a course list behind it. Some of them are all in one department, but most of them actually have courses that cover multiple departments. So human and population health has some courses in public health, but also some courses in biology. And so, they're not really aligned with particular departments, but they are aligned with areas of study that include data science. And so they get a course list and the student fulfills the domain emphasis if they take 3 courses in that course list. That's some of them. That's the rest. We're busy trying to set up a new one in aerospace. Yeah, we'll see what else pops up.
So the courses in the domains, are they primarily just courses that already exist and offered to the majors, or have they been in any way modified to include data?
Yeah, great question. So do the courses here, were they designed for data science students or have they been modified? Most of them have not. The idea of a domain emphasis is just learn about cognition or robotics or something like that. A lot of them do include some amount of data analysis just because that's how these fields are. But at the same time, they don't typically have data science courses as prerequisites. And so the students who are studying data science are mixing in with students studying lots of other things on campus, which I think is actually a nice feature.
Just to follow up on that, is, for example, linguistics, is it a subset of linguistic courses that would fulfill the requirement, or is it any?
Yeah, good question. So for linguistics, is it a subset of courses that were chosen because they have something to do with data? It is a subset. Not all of the courses include like a data analysis component. Sometimes you just have to learn about phonology in order to learn the background. But yeah, each one of these was developed by sitting down with some faculty member in the area and considering all the different courses that were out there and figuring out which ones made sense. And then there's a committee to review them. So there is some thought behind what counts and what doesn't, but yeah, but it's pretty large subset. There's a minor. Oh, go ahead.
So like comparing you guys to some of the other big MDs, like relatively speaking, you're less theoretically heavy, less like hardcore software engineering heavy, right? It's more like the domain that kind of thing. What's like again when I talk about university, they sort of say, well, if you go more that direction, maybe your students aren't as prepared as if they went to like a more hardcore, theory. Like, what was your argument or your ideas for doing more?
Yeah, good question. So kind of what's the design philosophy for putting together a program like this? We did want to make sure that students were set up for either graduate school or for kind of, some kind of work that sort of counts as continuing education. So something where they could be productive with what they've learned. Beyond that, I don't think we wanted to produce just one kind of student. I think one of the big goals was to make sure that this was a major that allowed students with a variety of different interests to learn something foundational so they could pursue those interests, but not to be too prescriptive about exactly what they're studying and what their focus and passion is. And so for that reason, the course list, it's as long as a typical major at Berkeley, but potentially we could have tried to make it longer and required more content, or we could have been more prescriptive about what the electives look like. But we wanted to set students up so that if they got really excited about, software engineering side of data science, that certainly counted toward the major, but it wasn't required. If they got really excited about the statistical inference part, that counted toward the major, but was not required that you take every course in the upper division statistics list. And just provide enough flexibility to let students choose what they want to do. Now, typically students take more courses than are what are required. So that's what happens in practice is that students go a little bit deeper than we force them.
Related to that, do you have an estimate of where these graduates have gone, like what they do? Like graduate school versus industry versus whatever?
Yeah, good question. So where do these students go? What do we know, Laura? Okay.
Can I amend this?
Well, I'll say that there's like a first destination survey that's public that we could point you to if you really want to follow up on that question that shows like what companies they go to. And there are a lot of students going into tech and finance and things like that because they're popular Berkeley wide. the students definitely going to graduate school. It's pretty typical that students going into graduate school will have double majored in data science and, astronomy or something like that. So they have that kind of deeper foundation in the domain than you would get from just a domain emphasis. But it really depends.
I want to amend this question a bit. So one of the things that was happening around like 2017 or 2018 is you talk to a company, you ask what kind of data scientist they want, and it's invariably somebody with a PhD in chemistry or with a master's degree. And so one of the things that was so great about Berkeley, say, we are going to do data science for students, is the potential to break this glass ceiling, because now that there are undergraduate students with a degree in data science from Berkeley, the hope was that the companies would reassess their hiring policies and consider hiring students with a BS degree in data science. Have you seen like this actually happen? Have you seen companies who start taking on as their junior data scientists students with BS degrees?
Yeah, good question. So have companies started hiring people with a BS or a BA, we give a BA, in data science into data scientist roles? I think the answer is yes. But they're still hiring physics PhD students. But I think the world is starting to run out of those, and this is looking like a pretty promising source of new employees. Question in the back?
For the complex sequence, it is a part of not calculating
Yeah, good question. What about the calc sequence? At Berkeley, since it's a semester system, there's really just a standard 2-semester year-long calculus sequence. The thing we don't require is multivariate calculus, but a lot of students take it anyway, because it's a prerequisite for some of the electives, and so they take it for that reason. Oh. Yeah, good question. So how can we help community colleges support this lower division? This is a Java course, but often is fulfilled by a C++ course that covers the same topics. And so a lot of community college students come in with credit for data structures already. So this is a course that typically is available in community colleges. Our programming course, we're a little bit more particular. So we teach it in Python here, but we spend a lot of time on higher order functions and recursion and how, basically how to express yourself in a way that leverages functions to their fullest potential. And this looks a little bit different than a lot of the community colleges courses that introduce programming. And so there's some work to do to see if we can figure out how to align what we think of as intro programming with what's often taught in California. And that's a project I'm excited about over the next few years. I do have to wrap up now, right?
Ramesh is not here.
Oh, okay, great.
Why don't you
Ramesh,
keep talking?
I'm gonna take an extra 2 minutes and answer some questions.
Python programming to Java data structures.
Good question. So is there a jump from programming in Python to doing data structures in Java? Yeah. And the way that it's handled is that the data structures course is just packed with content, because it teaches you all about Java, and then we teach you all about data structures and algorithms. And it's just like a very intense course that students actually love. I think more students say it was their favorite course they took than any other course. But also some students avoid until their senior year because they're terrified of it. It's like it's sort of a unique experience. A lot of students who take data structures course in community college are asked to take like a 1-unit bridge course that just includes the projects from our data structures course, because they're unusually large and involved, and we want to make sure students have that experience of kind of large scale software engineering. So yeah, it's a big jump and a lot to ask of students, but they get something out of it as a result. Okay. Oh yeah. Okay, well, last one.
Yeah, I really apologize for asking all the questions, but this is really important to something. So
Can I just?
one of the things you mentioned, there is that the multivariate calculus is required. I guess the way to think about this is one of the core concepts of machine learning, perhaps.
So I'm gonna just.
Machine learning is operations.
That's okay for you.
Optimization of a multivariate function.
Can we bring it up?
So. Where
Yeah.
do the students see something like this? Does that get?
Yeah, good question. Like, where do I learn what a gradient is and how to optimize this?
No, it's here. So just like look here and make sure that can see you and stuff. Let's get this figured out. Ah, shit.
Well, if they don't all take that course,
Ah.
sometimes they take a linear algebra course that doesn't really involve differential calculus. At which point they have to kind of learn it on their own, and that can be rough. We do some tutorials at the beginning of Data 100 to help them with it, but that's not a perfect solution. So I think the ideal case would be when you learn linear algebra, you also learn about.
Do you want to? Sorry, that's the wrong place. Keep talking. He's bringing up his demo.
Okay, well, what?
I'll do it. I'll do it at the end. Wait, I'll just start with that.
Okay, I'm gonna pull this over to here. And I'm gonna go like this.
Thank you. And Laura's our
And I'm gonna
director of
get
advising
this.
and it's wonderful. So thanks for coming up with answers.
There's a couple comments in the chat. One is, what is a data scientist? A statistician who lives west of the Mississippi. All right, there's some comments in the chat. Ramesh, so without further ado, segueing over to Ramesh, who is teaching Data 102.
Great. Hi, everyone. My name is Ramesh. I am a lecturer here at Berkeley, and I'm going to talk to you about Data 102, our senior level data science class, kind of for students kind of towards the end of their data science career at Berkeley. A bit about me. Oops. I am a lecturer at Berkeley, which means I teach part-time. I also work in industry doing kind of machine learning data science projects. So I tend to come at things from a slightly more practical bent, but that's not to say I don't value the use of theory to ground it. So I really like to emphasize in my teaching kind of the blend of theory and practice. Okay, so I want to talk about the course overview, tell you a little bit about who our students are, where they come from, what their background is, what the prereqs for the class are, then talk about the content, kind of a little bit about the pedagogy, and then I want to do a demo of one of our labs. And of course, Q&A. I'd love to keep this interactive. Feel free to jump in at any point if you have questions, thoughts, comments. I'd love to keep this pretty interactive. Okay, so student background. So this is kind of a capstone class. Most of the students who take it are graduating seniors. They generally tend to be, have taken a lot of other classes. Some of them have taken actually some classes that overlap with Data 102, but it's a pretty broad range. But generally, want to think students towards the end of their time as undergrads. The prereqs. So the first prereq is Data 100, which I think you'll hear about in the next session, which is kind of an intermediate level class covering kind of not the foundations that you heard about in Data 8 yesterday, but more one step up from that. Really understanding linear regression, multiple linear regression, what is a loss function, what is feature engineering. It also teaches a lot of like pandas, SQL, exploratory data analysis, visualization, and so on. Stuff that's not as relevant to Data 102, but is certainly very important. You'll hear about that in the next talk. They also come in with one upper division probability class. So this is a class where they really learn what is a random variable, what is a distribution, what is a density, how do you compute probabilities, what does independence mean, thinking about the relationships between multiple random variables, what does one tell you about the other, really a strong mathematical background in probability, essentially a first upper division course in probability. One thing I will say is that student proficiency does tend to vary. Some students come in and, a small number of students come in and they've like mastered everything in the prereqs. Some students come in and, they have forgotten how to compute a probability that, an exponential random variable is between A and B. So there's a pretty broad range of how well people have absorbed the prereqs. So we do have to make sure to reinforce things. And for a lot of the topics in the class, for a lot of the prereqs, I should say, this is only the second time they're seeing it, right? They learned it in the prereq class. This is the first time they're seeing it applied, right? So we really have to spend time on kind of brushing up the fundamentals as we build on them. Okay, it is meant to be a pretty challenging class. Students find it challenging, but they don't find it impossible. Student feedback at the end tends to be, this class is hard, the assignments are challenging, but I learned a lot, and I really appreciate this class. Generally, most of the content in the class is only covered in graduate courses, and I'll talk in a sec about the actual list of topics. But when you see the topics, you'll think these are usually graduate topics. And so we have to adjust how we teach them. We don't expect our undergrad students to be grad students. So we have to adjust how we teach them so that students can actually learn and get a foundation and sort of take the ideas in this class and then build on them whatever they do next, right? If they go to graduate school, then they take another class and they've seen the ideas before, they think in better. If they go into industry, they have familiarity with the concepts as they go to apply them. Let me actually just pause for questions here. Anybody have thoughts, comments on the prereqs? Kind of where student background is? Yes. I think kind of in between. John, would you classify Data 100 as a sophomore or junior level course?
Junior level course.
Junior, okay.
That was the design.
Okay.
Some people think it's a sophomore year.
Cool.
Mentioned efficiency varying widely. Are you just anticipating what kind of review or supplement, or do you have anything built into the course going to detect what they're bad at?
Yeah, so the question for folks online is do we know what students are gonna be lacking in when they come in? Do we have specific review items? We do. We actually have weekly sections that are just focused on covering prereq material. So we have a TA actually just take questions from previous classes and go over them and run through them so students can catch up. And it's usually a pretty targeted list because we know what students are going to need, and we know from teaching the class like what they're going to struggle with. Okay, cool. So I really think of this class as having 3 pillars, right? Because students have to come out of this class and be able to go into grad school, industry, wherever they go next, and take the ideas and apply them. So I think the pillars in no particular order. One is mathematical depth. They need to really understand the theory. They need to understand how to do mathematical manipulation with probability. They need to understand how kind of the basics of how do you do a proof. And they need to understand how the theory informs our algorithms, right? Why we do things the way we do, why we build our algorithms the way we do, depends on the theory, right? The analysis that we get out, the guarantees, the theoretical, the regret bounds, and so on, depend on the mathematical foundation. The second is computation. Students need to be able to take the ideas in the class and translate them into code, right? Understand how do I actually code this up, work with a real data set, implement something, get some results, and interpret them. And the last is really sort of intuitive understanding. Taking the results, my model, the output was 36.42. What does that actually mean, right? How do I interpret that? How do I communicate that to other stakeholders? I think a core thing in being a data scientist is being able to collaborate with stakeholders who come from a wide range of backgrounds, domain knowledge, expertise, and so on. And so being able to communicate clearly the results, the assumptions, and everything is critical. And so I think in every assignment, in every lecture, generally in the class, we try to balance these three, right? So students sort of have some exposure to all of these for each of the ideas that we teach. So what is the course actually about? Right? I feel like I've stood up here for a while just talking about it. Here's what we actually cover. This is actually a slide that we put up on day one. And I tell students the course has two big ideas. The first is making decisions under uncertainty. So understanding, okay, sure, I know how to use this model, but how does that actually translate to making a decision? How do I make a decision using the output of this model or the output of this technique? And then how do I understand the uncertainty involved? And that's like, this is a prediction. Here's an interval around this. Here's some variation, and so on and so on. The other kind of key thing is understanding the assumptions that underpin the techniques that we see in this class, but also the techniques that they've seen before. And thinking about how robust are the methods to those assumptions and what happens when those assumptions break down. And I tell students these are not new ideas. They've seen them before, actually starting in data 8. You probably saw in the session yesterday, these ideas of like decisions, uncertainty, assumptions, they come up in data 8, they come up in data 100, they come up in all the other classes that students take. And so this is not new, it's just these are kind of the central glue underpinning the pretty broad range of topics. Because you can see here, we cover a lot of stuff, right? There's a lot of different topics. And if without some kind of glue, it can just sort of feel like, here's this, here's that, here's this, here's that. And so having this sort of central thing for everything to glom onto, I think helps students kind of keep track of everything and fit everything into a cohesive narrative. I don't necessarily want to read everything on there. I'm going to focus primarily on the first four, just because that's what we spend the majority of the class on. So we start by talking about repeated binary decision making. What happens when you want to make just not one decision, but multiple decisions, right? And the simplest kind of decision is a binary one. We talk about Bayesian and frequentist modeling. We spend some time on predictive modeling, kind of linear, nonlinear, non-parametric, making more, fewer assumptions, understanding that spectrum. And we talk about causal inference. And I'll actually spend a whole slide on each of these. We also have a fairly comprehensive, well, for the relatively speaking, session on making repeated decisions with feedback. So this is essentially multi-arm bandits and reinforcement learning. And then we cover kind of a range of other topics: concentration inequalities, privacy, a little bit of economics. So it's really a broad course that's meant to give students a foundation in all these areas. I tell students at the beginning and at the end, you can take multiple semester-long classes in each of these areas. So we're not aiming to give students, here's everything you need to know. It's really more, okay, here is a foundation in these ideas. Okay, so we start with binary decision making. And for each of these, I'm just going to talk about like, what is the big idea? What is some vocabulary that they learn? I'm going to assume that most folks here are familiar with most of these concepts. I'm happy to like stop and explain, but I do want to be conscious of time as well. So I'll talk about the big idea, kind of the vocabulary, some of the techniques they learn, and just talk through some examples of what kind of assignments they might be able to do after each one. And then at the end, I want to do a demo of a lab that students see on causal inference. Okay, so with binary decision making, kind of one of the big ideas here is, how does our choice of error rate affect the decisions we make, right? So we want students to be able to understand what is a true positive, false negative, and so on. We want students to understand what's precision, recall, and what do they actually learn? They learn about multiple hypothesis testing, right? Why do you need something like Bonferroni correction in the first place? What is the Benjamini-Hochberg procedure? What is false discovery rate? What's an ROC curve? What's the precision recall curve? What's the difference between the two, and why does it matter? Right. So we have students think about, true positive rate, where your denominator is essentially the actual true decisions, versus the false discovery rate, or recall where your denominator is, or sorry, precision. And see, I tell students I always get these mixed up, even though I've been doing this for so long. So I tell students you don't need to memorize any of this. You need to be able to look them up though. Where your denominator is the decisions you made, right? Do you care about, having 95% of the decisions that you made, of the times you said, yes, there's something here? Do you care about 95% of the time getting that right? Or do you care about 95% of the time when something's actually there, getting it right? And like, what is the difference between those two? Why does it matter? We spend a lot of time on examples to really drive that home. An example of an assignment, one of the questions on the homework for this is they test 5 different hypotheses and kind of explain the difference between, different cutoffs, right? Using Bonferroni correction, using Benjamini-Hochberg. We do a little bit of like online decision-making with an algorithm called LORD, where you make a decision, you see whether it was right or wrong, and repeat. It's really just a taste to get students set up for what's to come later. Okay, questions on this? This is like 4 lectures worth of content that I just condensed down to one slide. So I obviously can't do it justice, but any sort of broad questions on the topics covered? Yeah.
So what's the balance between the more theoretical in terms of the assignments and the more practical application of, implementing or using techniques that you talked about?
Yeah, so the question is, what's the balance between theoretical and practical? So as an example, the homework that covers this, so we do homework every 2 weeks, one homework every 2 weeks. So the homework that covers this stuff, the first question is kind of entirely theoretical, doing kind of calculations with Bayes' rule, manipulating probabilities, kind of deriving a Neiman-Pearson cutoff, manipulating random variables and so on. The second question is kind of an interpretation question. It's sort of analyzing a paper about racial bias in police stops, where the paper kind of makes some particular assumption about the null, the distribution of the null hypothesis, and the students have to critique and evaluate that. And the third question is this one here, where they test a bunch of hypotheses. So it's very like practical, actually implement it, go work with the data set, run your simulations and see what you get. So I guess the answer is like all of the above, but in small doses because we only have so much time. Yeah.
Is there a programming component, for example, when you get to the bandits?
Yeah, so there's programming components throughout the entire class. So every unit has some program. So this assignment right here is actually a programming assignment. So we give them a CSV of data and we say, go take this and implement these. And one difference from a lot of other classes is we tend to not give students much boilerplate code, right? So we kind of, here's the question, now go and do it, right? Which is kind of a step up from what they've seen before, where usually, like everything is neatly filled in and if they just have to write the one line. Here, they really have to do everything themselves. Some of the harder questions that we do, we give them more setup code, but most of the homework assignments, we have very minimal kind of scaffolding code for students to work with, which students find challenging, but I think is important for them to experience before they go on to do this in the real world where there is no scaffolding code.
Set that at the outset of the course, especially considering the other classes really do have that code programs.
Yeah, so the question is, how do you tone set that? I think we just communicate that to students up front. We offer a lot of help, like all the other courses. There's a heavy office hours component. We really emphasize to students, if you get stuck, come ask for help, right? Attempt it, try it, get stuck, and learning happens when you get unstuck. So come talk to us. We have a lot of office hours, especially around the homeworks, which are very challenging. So we tell students, look, you will get stuck. That is okay. Ask for help when you do. Yes.
How do they submit the assignment? The grading process.
Yeah, so the question is, what is the submission process? It varies depending on the assignments, and I'll talk a little more about it when we get to the assignments. For labs, we have this autograder system, which I think people have heard about.
Has been teased.
Okay, so you will hear about AutoGrader, which is what we use for the labs. And for homeworks, we just ask them to submit a PDF, right, with their handwritten stuff and a PDF printout of their notebook. Yeah. So generally for the homeworks, we don't like test their code. We rely on looking at the output of it. Okay, so let me continue. So that's the first sort of module or unit in the class, binary decision making. The next is understanding Bayesian and frequentist inference, right? So thinking about Bayesian modeling, frequentist modeling, what's the difference? So we start with a simple maximum likelihood example, kind of go, turn it Bayesian, turn it into maximum a posteriori, understand how using a prior can help us, right? I think the example we start with is like product reviews, where you see one product that has 19 positive reviews and 1 negative review. You see another product that has 3 positive reviews, no negative reviews. And all of us, we look at this and we're like, I want the one with more reviews, even though it's only 95%, instead of the one that is 100%, but only has 3 reviews, right? Because we bring some intuition, that there is, the more reviews, they're better, and the product with no reviews seems a little sketchy, right? So that sort of intuitive understanding that all the students have of, shopping online and looking at reviews, we bring that in to help motivate the idea of a prior. Right, so we start with these very grounded examples to help students understand what's the point of doing this stuff, so that it's not just sort of abstract. Here's your, your conjugate prior and your exponential family and the information geometry. Because again, these are undergrads, right? They don't necessarily have the depth of kind of mathematical background to really understand all the theories. So we want them to have just a foundation. Things they learn, what is a likelihood, priors, posteriors. Again, this is Bayesian and frequentist, but it's really like focused more on Bayesian modeling, since most of their other classes are focused on frequentist modeling. So we talk about sampling as a way of doing inference. We talk about Gibbs sampling, Markov chain Monte Carlo, Metropolis Hastings. And we really start to introduce this idea of conditional independence. What does that mean? Why is that important? When you set up a model, why is it important that these things are conditionally independent, which also helps set us up for causal inference down the road. They learn about conjugate priors. They implement rejection sampling. They implement Gibbs sampling in code. They implement Metropolis Hastings. And one of the homework assignments is using Gibbs sampling to denoise an image. So we give them this like very speckle, noisy image, and ask them, okay, implement a Gibbs sampler. Here's your distribution. Here's your prior. Here's your likelihood model. Neighboring pixels should be similar. Go and implement a Gibbs sampler to denoise it. And they denoise it, and they're like, wow, this is cool. I did this. I actually did a similar assignment when I taught an undergrad class like 11, 12 years ago. I think then students were like blown away by the assignment, but of course now, with the technology available, I think students are still impressed because, you don't need any training data to do this, but obviously it's not as impressive as it once was. But students still enjoy it. They have to model synthetic data with a mixture model, right? So we understand what is a Gaussian mixture model, kind of variations on that theme. And we use PyMC3 as the computational framework for that. So PyMC3 is a sort of Bayesian computational thing. If you're familiar with Pyro or NumPyro, it's very similar. Essentially, you specify your probabilistic model, and behind the scenes, it uses the Hamilton-Monte Carlo sampling algorithm to do everything. So we kind of have this as like a black box. Here's just how it works. Here's what you can do with it. Okay, we spend some time on predictive modeling. Again, the big idea here is like, what are the pros and cons of making more and fewer assumptions, right? So on one end of the spectrum, we have like generalized linear models where you have a model that's like mostly linear, right? You have, linear interaction between your features and predictors, and you have to do feature engineering if you want more nonlinearity than that, and you have some nonlinearity that sits at the output. On the other extreme, you have something like a random forest or a neural network, right? And so we kind of give students the spectrum and understand, well, making fewer assumptions, throwing a random forest at it might solve the problem better, but you lose something valuable in interpretability along the way. using a GLM might, be perfectly interpretable, but if it's not accurate, then, it's not actually useful, right? You can interpret a model that's completely wrong, and your interpretations aren't useful. So we kind of give students that spectrum, that trade-off, and have them explore it. There's some lab assignments, some homework, and so on. And we spend a lot of time diving into quantifying uncertainty and model checking goodness of fit for both frequentist GLMs and Bayesian GLMs. And a couple examples, they explore the effect of different priors on fitting a GLM in the Bayesian setting. And they kind of compare and contrast interpretability versus accuracy of GLMs versus random forests for a simple data set. We spend some time on causal inference. Again, here, this is not meant to be, a total, comprehensive coverage of the topic. It's really what we can get through in 3 lectures, right? So they've seen some of these ideas before, in data 8, they learn about randomized experiments and why you can draw causality from randomized experiments. What assumptions do you need to make in order to draw causal conclusions in non-experimental data? So we talk about the potential outcomes framework, the kind of structural causal model, causal DAG framework, and kind of introduce both of them as complementary. We talk about unconfoundedness, assumptions and so on. And they learn matching, they learn outcome regression, they learn propensity score weighting, they learn about instrumental variables, and they implement all of these, right, on a homework. And as examples, we found a paper that evaluates the COVID vaccine, both the efficacy and the rate of side effects. And using matching on this large data set. I think it's a paper out of Israel. And we asked them, go read this paper, interpret it, understand it, explain it, and what method are they using? Is that a good choice? Why is it a good choice? And so on. Then they implement propensity score weighting on this data set of child development to measure a causal effect in observational data. I'm going to go pretty fast on the last few because I know I'm at time. We cover bandits and reinforcement learning. We cover a whole bunch of other topics, markets, privacy. We spend some time on concentration inequalities, like one lecture going really deep into the theory, Markov's inequality, Chebyshev's, and so on. And then I like to do a lecture entirely on case studies, essentially real world examples from the last couple years of course content being applied, some of the pitfalls, some of the kind of interpretations. And a lot of these are kind of drawn from controversies that students might have seen. So I think students really enjoy this as, oh, this is what this looks like in reality. Course components. Oops, not sure how this happened. There's lecture, which is twice a week. There's lab, we have discussion, and we have homework. So homework, as I mentioned, is pretty challenging. Lab tends to be pretty easy. It's very guided. There's a lot of hand holding. It's take this concept you learned and translate it into code, right? We give you boilerplate, we give you scaffolding. You just have to fill in and understand how to implement this equation in a couple lines of code. We have discussion sections where TAs cover problem solving examples. We have 2 midterms. We have a final project where students work in groups of 4. They pick 2 of the modules I talk about, each slide. They pick 2 and apply it to a data set. We give them a couple, they can bring their own. It's really meant to give them hands-on practice in a somewhat controlled environment. It's just a project. We tell them, we don't expect this to be something at the level of a publishable paper. It should just be, you should apply the techniques correctly. And where they don't work or where your assumptions don't work, you need to understand and interpret and discuss that. The class is taught usually by 2 co-instructors. We have it's usually 250 students a semester. We have about 5 to 7 TAs. They generally are master's or PhD students. We have 2 to 3 readers who grade and hold supervised office hours. And one of the challenges of teaching this class is that the breadth of the syllabus does make it hard to onboard staff, right? Not every PhD student knows a lot about all these topics. Obviously, students who are alumni of the course are great for this, but non-alumni generally, need a little bit of catch up or hand holding in one area or another. I know I'm over time. I was thinking about doing a demo, but I think I might skip just so that I don't ruin your schedule.
Lisa's there waiting.
Okay.
I don't know how to wrap it up. I think she's ready to be.
Okay, I'll wrap up then.
Okay.
Maybe I'll just ask for questions while she's getting set up. Questions? Yes.
So cover like a ton of topics, a lot of them have huge background, like the Bayesian one for the semester, right? So what made you guys decide to do a broader one versus bigger, smaller topic?
Yeah, so the question is, these topics could each be a whole semester. What made us decide to go broader rather than just cover a few of the topics? From my perspective, I think it's helpful for students to be exposed to all of these ideas. From my own personal experience in industry, I feel like I have used each of these topics within the last 3-4 years. And so I think it is helpful for students to see all of that and be exposed to that before they graduate. And so this is really meant to do that. I don't know, John, do you have anything to add?
Yeah, I think this was the list of topics that we felt like data science majors should know when they graduate, and that was a lot of motivation for the design.
So I have a lot of questions, but I'll ask very quick ones. For the lecture where you talk about case studies, do you have a list of case studies that you okay sharing for those of us who people case studies to share in our classes?
The question was about the case studies. Do I have a list that I'm willing to share? Yeah, I have. I'm happy to share the slide deck, which has slides on it that put it in context, and also links to articles and papers as well. I'm happy to put that in the
Slide deck's on mine in the schedule.
I'll add a link to that slide in my slide deck. It's not there now, but I'm happy to.
It is data102.org.
Yeah, if you go to data102.org, you can find the course content and slides as well. Okay.
Thank you. Awesome presentation. One more. We're gonna go on to Lisa. So yeah. Okay. That's fine.
Is it fine?
Looks good.
Okay.
Let me move this off. But carry on. Okay, just keep an eye on the owl.
The owl. All right. Hi, everyone. Good morning. Hope you all had a wonderful first day and a good first hour of the second day. Today, so yesterday I talked a little bit about Data 6, which is an entirely introductory course. Today I'm going to talk about Data 100, which is not really an introductory course. It's something that that students here usually take in their at the end of their second year, if not the beginning of their third year. So I'm going to give some context for this course. Here we go. Okay, so I'm going to give some context for why this course exists. I've been the instructor for Data 100 for 2 years now, but it's been around for the last 5 or 6 years, I believe, at UC Berkeley. So I'm an assistant teaching professor, and my PhD was in presenting data and analyzing data in an education setting over 3 different degrees: bachelor's, master's, and PhD. And it turns out that all of the skills that I learned across these 3 degrees are now all concentrated into one course. And that's kind of the beauty of data science. Is it's not something that we really had a name to for the last decade or so. And then now we finally have not only a name to it, but also a degree program around it. And so I think this is a very, very valuable course for building that very applicable experience, that industry experience, research experience, all of these types of things. So Data 100, we call this Principles and Techniques of Data Science because it really is Principles and Techniques of Data Science, which is slightly different from the Data 8 approach. So there's kind of 3 learning goals. I don't know where my notes went, so I'm going to keep looking this way. I apologize. Actually, there we go. Yeah, that'd be great. Fantastic. Yeah, I messed up when I clicked the button.
Yeah, you did.
Thank you. So there's really 3 learning goals here. There's prepare, enable, and empower. And that's kind of how I think about it, because I do really like to have kind of a student first approach when it comes to teaching. Thank you, Eric. And what I mean by this is that because Data 100 comes later in the undergraduate curriculum. At this point, the students are starting to think about industry, they're starting to think about research. We want to be able to prepare their data science skills and train their data science skills, thank you, for real world problems. So kind of putting the animation here on the slide. Oh, there we go. Yeah, thank you. Is to start working with all these different aspects or these different dimensions of data science, including management of the data or engineering of data a little bit, machine learning, statistics, real world data, and again, thinking about this in the context of real world problems. And so for the rest of the presentation, I'm going to kind of show you a few of these examples. I'm going to show you how we go from data 8, which is a few courses prior, to the data 100 topics and what the relationship between these two things are. So this is a revamp of probably John's slides from earlier this morning. But if we think about data 100 in the context of the major and minor here at Berkeley, data 8 is foundations of data science. That's students' first exposure to data science, maybe first exposure to programming and this type of statistics. And then data 100 is actually one of the required courses for the data science minor. And it's kind of on the path to a lot of our major oriented courses. So Ramesh earlier was talking about 102. 102 is something that happens after data 100. And data 100 is part of this like what I call early upper division, but it's really the core skills that are needed, not just for the minor, but for data science in general, including, well, data 100, probability, as well as human context and ethics, which my colleagues are going to talk about in a little bit. For data 100 specifically, I mentioned earlier that it is a class that students take in their late sophomore, early junior year. And this is because after data 8, students do more programming. So they build up their programming skills and they also learn more mathematics. So they build up their linear algebra skills, their calculus skills, and then they kind of integrate all of these together into the data 100 course. So let me show you kind of how all those skills come together in what's called the data science lifecycle. This is something that we partially address in data 8, but we just call this out from the very first day in data 100, which is that when you're a data scientist working in the real world, there are all these different phases of data that you are going to work with. First of all, there's the question itself. Sometimes the question is given to you, but you still need to formulate the question somehow. Then there's acquisition of data. Again, sometimes the data exists, but you need to think about, okay, what does it mean to have this data? Is this tied to the original problem that I wanted? And so on and so forth. And then there's this exploratory data analysis phase, which is, okay, in order to answer that question of whether the data that you have is relevant to your problem or is directly going to address your problem, you need to explore that data. And that involves a lot of data wrangling, data cleaning, all these types of things. Now, if you're going back to actually try to answer the question that was originally posed or that you posed for yourself, you need to think about modeling and prediction and inference and all these things, just kind of like exposing that a little bit, exposing models before they move on to other more advanced courses like 102. And then finally, there's a modicum of, well, as a data scientist, you need to actually export the things that you've done. You need to translate a lot of the things that you've done to other people on the team. How do we report? How do we make decisions? And how do we kind of come up with solutions to answer the original question? So data 100, we introduced this cycle, but because it is quite a large class, we often focus on just the techniques and the principles that are needed. And so I kind of like to say that I really zoom in on the acquisition, the exploratory data analysis, and the prediction and inference components. So really like the computational and statistical tools, similar to data 8. But just like, okay, these are tools that we need to work on. This is kind of a technical class. And then the rest of the data science major is built around formulating questions, acquiring a little bit more data, really thinking about this top arrow right here a little bit more. Yeah, that would be later on in the curriculum. But if we move on, what are different tools that are introduced in Data 100? So again, the idea here is that we want it to be practical directly for industry, directly for academia. And so we move from the data science library, the Python library that's in Data 8, and the single notebook that students are using in Data 8 to the Pandas library and to SQLite. Still using Python as kind of a base for introducing a lot of these concepts. Our SQLite is actually like a very well, anyway, we can talk a lot about the SQL part later. But anyway, so the idea here is that the data science library introduces tables, arrays, all these different components. But it's really like, that's like a Berkeley specific thing. That is a library that's specifically made for education. And then now we introduce pandas as a way to say, okay, this is something that the industry expects. This is something that will be a lot more powerful for you to use. Also, there's a bunch of documentation. How do you read that documentation? How do you work with a lot of these methods? That's something that we teach in Data 100. From the Jupyter side, we go from the single notebook to the Jupyter lab. And so now instead of just working with one notebook where everything has been provided for you step by step, we say, okay, actually, no, there's like this file, like there's this folder of a bunch of different data sets. Some of them are in CSV, comma separated files. Some of them are in tab separated files. Some of them are in JSON, all these different types of things. How do you actually take this messier data and bring it together, like work through a different file system, all of these different components here. From the EDA side, again, we go from the visualization items of the Data 8 Python library, so histograms, bar plots, all these things. We try this again in Matplotlib, Matplotlib, and Seaborn. As Matplotlib and Seaborn get a little bit more arcane, we're looking to move towards Plotly a little bit more because that's kind of like that's more dynamic. It looks cooler for sure, but also has a lot of different features that are very useful to real world data science. Yeah, so we're working on a lot of the Plotly integration. But we build in more and more advanced visualizations that are useful for modeling more complex data or visualizing more complex data, including violin plots as an alternative or as an additional feature to bar plots, for example, or box plots, overlay histograms and trying to figure out how to put in all these features and so on and so forth. Yeah, I have kernel density estimates up here. These are kind of cool graphs, and so students love these graphs because they're like super cool. But they're also very useful for modeling things that or visualizing things that they weren't able to in Data 8. At the machine learning side, what we learn from Data 8 is that they start with NumPy. They start with things like linear regression, and then from NumPy we move on to adding in additional functions and additional functions and models from SciPy as well as scikit-learn, which is a very standard research machine learning package in Python. So we go from linear regression to something called least squares regression, which is roughly the same thing, but now we actually prove the mathematics behind it. Whereas in Data 8, they really got the intuition behind it. We move on to logistic regression, decision trees, all of these components that are very fundamental to a lot of data science from the very beginning. And then we move a little bit into unsupervised learning, not too much. We just kind of teach them that it exists. We do some standard clustering and move on from there. So in terms of real world data wrangling, like I said before, real world data, this is kind of a priority for Data 100 because we do want the students to be prepared for the stuff that they're going to do in industry as well as in academia. And so we really focus on the cycle of EDA and data wrangling back and forth. So for example, we have San Francisco data here for this. I believe this is Yelp data about where each restaurant is located. And as you can see, there's some wacko numbers here, latitude negative 9,999 and longitude negative 9,999. These sorts of values or placeholder values are going to be very common in data that, that students are going to look at. And this is actually something that happens in maybe week 2 or week 3, is that now suddenly they're dealing with a data set that has a bunch of different numbers, like for example, the negative 9,999 phone number. And then they have to be like, okay, this table, there's some entries here that I need to somehow impute the labels of, drop the rows of, and so on and so forth. Yeah, just highlighting it a little bit. Other notes here, so we do cover a lot of, again, different techniques. And so we include regular expressions, for example. We talk a little bit about the trade-offs between interpolation or canonicalization, or trying to make everything similar to each other, or imputing, inserting different labels in where things are missing. And then we do talk a lot about engineering different features for modeling. Let's see here. There's a few other points here, which I believe Ramesh might have talked about a little tiny bit, but we do start to dive into some of the principles that students will need to know for machine learning, because a lot of our students from Data 100 are very interested in machine learning. They want to at least be able to start engineering some models. And so even for models as simple as linear regression or logistic regression, we start talking about concepts like cross-validation, or leaving out some of the data to be able to evaluate whether your model is doing well. Gradient descent, so one of the key features behind a lot of the ways that our scikit packages work. And even things like the model bias variance trade-off, which is what they explore a little bit more in future courses. I put the one mathematical equation on here. We do start to introduce probability a little bit. So actually a lot of our students take the probability class at the same time as data 100, but just trying to get students around to understand the fact that the data that they have received is likely a sample of the population that they would like to study, and what that means for the probabilistic assumptions, what that means for the randomness, what that means of the conclusions that they can draw. These are all things that we start to touch on so that they could then kind of see it in their later upper division courses. So a typical week in Data 100 looks like what you might expect of an upper division course. There's 2 larger live lectures, about an hour and a half or so. There's a discussion section, and then we have a smaller lab due before a larger homework. And the idea here is that because our course is very application focused, is very technique focused, the lab is more like a tutorial for training through how to use a particular scikit-learn package, or looking at the initial part of a data set, and then the homework goes much deeper, has a few more open-ended questions, and so on. But yeah, so what I wanted to do right now is I just wanted to show you one example of how we move from something like data 8 into data 100. The spoiler is that for a lot of students, they've actually seen everything in data 100. Okay, sorry. Okay, they've seen 60% of data 100 in data 8. But it just hasn't been called out by name. It hasn't been entirely proven to them. And then data 100 is them revisiting the concepts and kind of like really showing that they do understand, they actually saw a lot more in their first year here at Cal. So for example, in data 8, there's this one entry from the textbook where we have the sea animal here, and we would like to model age versus length. And it turns out that if you try to slap a linear regression line onto this, it's not a good fit, right? Because there's this heteroskedasticity, right? And so the idea here is that from data 8, we just say, hey, the residual plot shows no good, an ideal residual plot would show no pattern. But this one, if you kind of plotted the prediction versus the actual values, there is indeed a pattern, right? And so this is not a good fit. This line is not a good fit for modeling age versus length. So this is where data 8 stops. And then data 100 brings back the same example, says, okay, this is where we stopped and we weren't able to go further with what we knew from data 8. However, for data 100, we want you to go further. We want to go, okay, even if this is a non-linear relationship, how would you actually model and fit this relationship? And it turns out that if you think about it a little bit, you could probably take the log of age, and that has a linear relationship with length. Right? And then so this is actually, and if you look at the residual plot a little bit, now there is no pattern, and so it's a reasonable residual plot. And then we kind of transform it back to this logarithmic curve. Okay, so like the second part of this, or like the, again, 60% or so, the idea of linear regression, the idea of residual plot, these are things that students have already learned from data 8. And we're going that one step further so that students can see how they can build on a lot of the problems that data 8 brought up in the first place. And so we kind of go through a lot of these things in our homework assignments. Again, focusing on real world data a little bit. We have things like food safety, which I showed you earlier. We have things like text analysis through Twitter. We're looking to actually change this. I'm going to talk about that in a little bit. Bike sharing, like what does it mean to actually use shared ride bikes, and how can we kind of explore that data in a city. IMDb for the SQL component of our course, and also voting, because political data is something that is very interesting to our students of 2023. And taxis, which is not as interesting to our students of 2023. So we also have a few projects which are considered larger homeworks, like multi-week homeworks here. I'm just going to put up these questions. I'm not going to read them out, but the idea here is that there's a lot more engineering. There's a lot more open-endedness of like, okay, we're asking you to build an email classifier that classifies things as spam or ham, which is not spam, right? And so how do you engineer the features to have a reasonable classifier? How do you design it? How do you reflect on it and kind of compare and contrast the classifiers that you've built so far? So where do we go from here? Like how great is data 100? It's pretty nice. I'm going to show you some student feedback here. So I'll just read some of these out. I honestly would consider this class the most useful class that I've taken here at UC Berkeley. I really appreciate how applicable this class was to just about everything. And then so again, the word applicable comes up again in the second quote. Really enjoyed the course, feel it's the most applicable one. And then there's a lot of students who use this class as kind of a pivot, a deciding point for where they want to go next. So for example, pursuing a data science minor, just trying to finish out the probability, the HCE requirement, the human context and ethics requirements. And then there's a comment from one of our graduate students here. So Data 100 is also has a fraction of graduate students who take the course. The graduate student says, hey, please continue offering such incredible courses, especially on the graduate level, because this is something that really meets, especially early graduate students, where they are in terms of the needs that they have. So where does the success come from? Personally, I think it comes from many passionate teachers. And so we have a graph here on the right. It's a little bit small, but this is actually the size of Data 100 over time. As of 2023, we taught 1,209 students, 91 of whom are graduate students. This is a very, very, very big number, right? And you can kind of see, I tried to use the blue and gold to match Berkeley colors, but it's grown over time. And so we really think that at least from the student engagement level, a lot of students are very interested in the course. Even at 1,200 students, we still had students who were like, hey, can I take this class? Can I take this class? And so that's nice. And then I'll point out another success in a little bit. But there's a large teaching staff, lots of interaction. So even in such a 1,200 person course, we do still have weekly discussions, labs, office hours, review sessions, class forum, which is highly engaged from the students, and also class live question, answer, and activities. And this is something that my colleague Nargis Nuruzi and I were thinking about this past semester. Is we want students to participate in class. We want them to show up to lecture, because otherwise, if we're lecturing 1,200 students, we'd like to actually see that students are, learning the material at the same time that we're talking. So how can we engage students in active learning? How can we engage students in keeping pace with the course instead of leaving everything until the last minute? This is something that we've been trying to do more from using tools like Slido, Poll Everywhere, and so on. There's a few other quotes here from about speaking latitudes of our staff here, full of content, but the staff are so supportive, right, in terms of all these different resources that we provide. And then the data science staff is the best amongst UC Berkeley courses. I hope this is true, but and so to me though, in terms of this idea of staff being the real bread and butter, I absolutely think this is true. This starts from our co-teaching team. So again, with 1,200 students, you might imagine it's pretty difficult to teach. So what we've been doing for the last few semesters is we've always had a paired team of faculty instructors or lecturers. And so usually we try to have a computer science and statistics, and we try to match it up a little bit. The last few semesters, it's been a little bit different. But actually, I'd like to point out that this past spring was the first time that we had 2 women instructors at the front of the stage, in which actually a lot of the students pointed out, and they're like, hey, that's super cool, right? That is not something that I saw in any of my other upper divisions, especially in a technical level, right? And so me and Nargis, we felt proud. But thank you. Yeah. But the other thing that I would like to say, and that I would like to point out, here's our textbook team, by the way, again, kind of bringing in people from different places, statistics. We have a PhD student, or a student who ended up going to do their PhD at UC San Diego, is now going to be a teaching faculty there, Sam Lau, who has contributed to the team, and Joey, who you heard from yesterday, is also there. But our teaching staff is also fantastic. And we also really try to bring in at least a gender diversity into our teaching staff. So actually this past spring is also the first time that we had a head TA who was a woman at the front of the stage, to be able to actually lead a lot of the logistics and to be one of the kind of the primary people answering some of the questions that the students are posing. Right. And again, that I just want to repeat, that doesn't go by the students, right? Or that is something that they kind of call out and they'll be like, hey, that's awesome, right? Or this actually inspires me to want to be staff. And it's unfortunate that my colleague Ania Dakari isn't here today, because she's kind of the mastermind behind all of this hiring stuff. We were talking a lot about undergraduate TAs. Ania always really thinks about, okay, how do we bring representation into the staff? How do we actually start changing who's at the front of the classroom, and how do we actually, have that be the motivating factor, not just for students to stay in data science, but for them to participate and contribute as part of the teaching staff. And that's something that we're always trying to work on. But yeah, so I think I counted the number of staff here. If you just look at it, it's 46 teaching staff plus 2 instructors. This is, again, I mentioned project management and program management. This is a large part of the job, but again, I want to stress this could not be possible without all these wonderful undergraduate TAs. And there's a few graduate students sprinkled in as well. So where do we go from here? Well, I kind of think, again, if we come back to prepare, enable, and empower, which are the learning goals that I put up earlier, we want students to balance theory with practice. And that's something that we do try to tie in, right? So again, they're coming with a mathematical background, they're coming with a more computational background. Data 100 is trying to marry those two together. Considering context at every step of the life cycle, this is something that we're working towards in our Data 100 course. We do bring in real world data sets, but I do think that we do need a little bit more reflecting of where those data sets come from and how they're trying to represent society. And then finally, building a new culture of computing that complements and enhances our other computing majors, since at least in the current form, data science does have a lot of computing in it at UC Berkeley. And so with this, I wanted to actually do a small teaser to what's going to happen after break, which is kind of our first examples of, or one of our more successful examples of how we try to marry the context with the computing and with the mathematics that we expect from our students, which is the Cook County Assessor's Office project. Our first project in Data 100 that comes about maybe like 40% of the way through the semester. It's the first time students are thinking about linear regression and trying to engineer a lot of the features to predict housing prices using property characteristics and sales data. This project is developed in partnership with our wonderful collaborators at HDF, who Cathryn, Carson, and Edmundson, who are going to be doing the session later. And as part of that, there is a lot, like we start with this question of like, okay, Cook County Assessor's Office, there's some housing prices here. Why is this such a big deal in terms of housing prices being assessed? What does that mean for the residents, or what does it mean for the property owners in that area? Where's the fairness here? Where's the bias? Where's the transparency? And we're moving beyond the idea of just modeling data to considering that the data is actually trying to tell us something, right? Or is trying to demonstrate a version of the world. And so that was my approximation at the pitch. But if you want to hear more from our wonderful experts in this field, definitely come back after the break and we'll talk about it a lot more. So with that was a whirlwind of what Data 100 is. Hopefully I gave you some really exciting ideas about how you might want to, see some of this material maybe in your own classroom. We are working, Eric told me to say this, but we are working on trying to make a lot of this material available for you in the same way that Data 8 is. But for now, I'm going to say, email Eric. But actually, the other thing that I will say is that if you go to our course website, ds100.org, all of the lecture slides are Creative Commons licensed for now. And one of the things that we're working on is from the assignment perspective, assignment solution perspective, how we provide it to instructors and I think we'll try to follow a model very similar to Data 8 in sharing that. So yeah, thank you. I'll take a few questions. Okay, I saw one in the back and I'll come to you. Yeah. Yes. Oh yeah, that's a great question. Fantastic question. Yes. Great question. Good question. So the question is, of these prerequisites, which one is the most important, and how can we kind of partition out this course a little bit more? Good question. I would say that Data 8, in terms of just seeing the material the first time, absolutely important. The second one that we find is very important because of the way that the course is designed is the computer science experience, the programming expertise. And again, I don't want to discount the statistics importance too. And so actually one of the things that we've been considering is, linear algebra is the way that we're trying to prove a lot of the different concepts in Data 100. But there's also this aspect of probability and random sampling that we want to bring in a little bit more. I think if there's more exposure in that direction, it would be good. Linear algebra is a little again, there's a lot of proof stuff that I imagine for different students, you could probably reorganize a little bit. But yeah, programming for sure. And I want to say probability, even though it's not technically a requisite here. Just in terms of like sampling, like trying to simulate a little bit more. Oh, good question. What programming is here? So this is a CS1 course, but the most important part is that it's in Python. And so it allows for students to know what for loops are a little bit more, for them to write functions, for them to have reasonable style. That way, when they're presented with some starter code, they can work with it instead of just having to implement 2 lines at a time. They can actually write 10 or 15 lines and debug that a little bit better. Yeah. Then we had a question in front.
Yeah, my question is sort of like on the same line, like if community college, we're writing like a associate degree for transfer and we have these courses, how do you feel the students that are taking Data 8 are prepared going into Data 100? Because now they're going to be taking at the community college level as basically their intro level math and then not seeing it for almost 2, maybe 3 years.
Yeah.
Data 100.
Yeah, that's a really good question. So just in terms of preparation, timing, that type of thing for community college. Yeah, so we do have a good amount of transfer students who take this course. And so I see them in their second semester at UC Berkeley. And so for a lot of them, they take, I mean, right now, because there's no data 8 at the community college level, they take data 8 in their first semester. They have a lot of the linear algebra and programming experience, right? So they jump straight into data 100, and they found that very, very useful. Is just like, that's already a reasonable amount of preparation. So as long as there's data 8 and as long as they have other exposure to programming and mathematics, I do think that they're ready for data 100. And in fact, a lot of the transfer students who stop by my office say, hey, I wish I could take this in my fall semester, right? But I had to take data 8 first. And I was like, oh, but data 8 is so important for you to take. So like, I think the more that data 8 can be at the community college level, the much more effective it'll be for junior transfers, especially since, at least based on a lot of the student evaluation we've gotten, data 100 is one of the most important courses for students when they're doing interviews for full-time or internship positions in data science. And so I think just being able to time that in the fall, if they're able to take the, like data 100 in the fall, would be fantastic. Yeah, good question. Yeah, there's one more here. Mhm.
The graduate students who take data 100, do you require that they do an additional components of the course? How is it different?
Yeah, good question. So for the graduate component of data 100, there's also a graduate project. And that's something that's relatively well scaffolded compared to maybe other graduate courses. I mean, because we have 90 students, it is a much larger graduate course than normal. So what we usually do is we have like students in teams of 2 to 3. They work on a larger data set, messier data set that we've kind of picked out ahead of time. And then they write midterm and final reports for it. But it's kind of like a 4-week, 4 to 6 week project at the end of the semester. Good question. Okay, well, I've gone over time a little bit. Did you have a last question? And then we can end with there.
I mean, it's similar.
Yeah.
With these questions, but like, I know a lot of our students, like, they take a class with us to kind of like, it's like test run one of their classes, like a street math class, they might test run before the week. Do you have enough students, you know, like what their repeatability is, like, students that retake this class at all, would it be beneficial for them to maybe just try it out?
I see. I would say we don't have many students who retake this course, just in terms of the challenge level of the course. I think the material is engaging enough and accessible enough, especially after data 8, that we don't get many students who, you know, I mean, sometimes there are students who it's like something happens in the semester and they decide to retake it, but it's a very, very small fraction compared to some of the lower divisions that we have. And so I think, yeah, if there's a version of this that can be offered at the junior college level, that is fantastic, right? Just in terms of really being able to prepare students for what they need from an associate's degree to even just go directly into industry. I think this would be awesome. If we could find some version of this that like gives you certification in some way, yeah, super happy to talk about it and try to fix something up. Yeah. So with that kind of like future collaboration note, maybe we'll break for a little bit and then we'll come back at 10:45.
That's correct.
Yeah, sweet.
Yep.
Thank you,
Awesome.
everyone.
Thanks, Lisa.
Hi, my name's Edmundson. I'm a lecturer in data science. I'm not a data scientist, I'm a historian by training, but I'm here to represent the Human Context and Ethics program together with my colleague Cathryn Carson. And we're gonna kind of break this up into a couple parts and tell you a little bit about what we do and what makes Human Context and Ethics, or HCE, at Berkeley unique. We'll tell you about the program, and that's what Cathryn's going to do in a few minutes, but I wanted to actually start with something more concrete, because that's a big part of what we do and what our program's about. Start with a story, tell you a little story, a case study, one that Lisa just sort of gave you a little preview of a moment ago, as an example of the kind of things we try to teach and the way we try to teach them, the kinds of styles of thinking we aim to help students learn to become basically more responsible data science practitioners. It's a case study, as Lisa kind of put up there, that we originally developed for Data 100, but it both exemplifies things that we do across our dedicated courses, such as Data 104, and it's actually a case study that we've incorporated into some of these other courses. After I go through this example, Cathryn will tell you a little bit more specifically about the broader program, the specific classes we teach, the underlying theory behind it, why we do it. But I'm going to start just by running through this kind of case study as an example. Okay, so as Lisa hinted at a moment ago, there's this case study about the Cook County Assessor's Office. Now, this originally began because we were looking for ways to bring more interesting context into Data 100. A few years ago, this back in about 2019, Data 100 had a homework that involved modeling and predicting sale prices of homes centered on a well-known data set in Ames, Iowa. Some of you may teach with it. But it was very much a data set that was constructed for the purposes of teaching data science and statistics and modeling. It wasn't so much drawn from real data that people were really using to do specific things with. And so we wanted to look at something that was even more of a real world and less of a toy problem to get students to learn to work with data that itself was a product of and very much entangled with real attempts by actual, in this case, a government institution to do something with data, to look for something with a more evident context and clear ethical stakes. So it was actually a student of ours working on our team. We have a student team that helps develop curriculum that was looking around and came across a story about an open data initiative at the Cook County Assessor's Office. Cook County, most of you probably know, but this is basically Chicago and some of the townships around it. Came across a story about an attempt by the assessor's office in Cook County to create a new sort of office of data science to basically predict housing prices better. And in particular, to do it to address a deep underlying social problem involving racial discrimination in the prior tax assessment system. So again, this is a living example of a project where students follow the path of an actual real world institution, try to replicate the results, but also learn more broadly about the context in which that institution operates and why it works the way it does, if it works at all. So just to come back to this, like predicting home prices, a lot of students think about that. And the first thing they think of, if they think of anything, for a lot of them, this is very foreign, is, oh, this is like, for something like Zillow, it's predicting real estate prices so you get an estimate of the price of your home. In a more, for the most part, in the way that actually housing property value prediction originated, it was in large part developed by assessors' offices. That is to assess the value of a home, even if it hasn't been sold in decades, so you know how much property tax to levy on it. And that's the kind of role that students that work on this homework step into the role of a tax assessor that has to figure out, how do I figure out how much tax to levy from not just an individual household, but households at scale, and really a massive scale when we're talking about Cook County. Okay. This is a little foreign, by the way, for California students, because our tax system, property tax system works differently, but we won't get into this. For most states, most counties, something like this has to work. And there's a whole expert institutions built around how to do this the right way. Part of the reason that this office was created and why it came to the attention of my student and how we got the data and everything to build this with was that there was a really massive scandal that was reported by the Chicago Tribune back in 2017, and a whole series of stories written by some investigative journalists together with experts at the University of Chicago that was about basically massive discrimination in the Cook County Assessor's Office and its property tax assessment system, really in roughly the decade prior to 2017. As you can see from this, it's a series called An Unfair Burden. And as they said, Cook County failed to value homes accurately for years. The result, a property tax system that harmed the poor and helped the rich, and even more disproportionately harmed Black and Hispanic property owners in Cook County, Illinois. That is, the disparities fell across both class and racial and ethnic lines. What was supposed to be a flat tax rate in practice was actually deeply regressive. And because of the deeply segregated nature of Chicago, oftentimes considered by certain metrics, the most segregated major city in the country, the formerly regressive system ended up disproportionately harming Black and Brown residents. And they demonstrate this in the story using various different kinds of measures. These are kind of official standards that come from an organization called the International Assessors Association, or International Association of Assessment Officers, to basically measure the different ways that property assessment can be regressive, unfair, inaccurate, basically different measures of accuracy and how errors are distributed, that they use to basically demonstrate not only that were these just deeply inaccurate, the systems overall, but that the distribution of these inaccuracies were deeply regressive. That is, the lower your property was valued, the more likely you were to be overvalued, your house to be overvalued, thus accruing a much higher tax burden. The wealthier you were, the more valuable your property was, the more likely it was to be undervalued. So this is, this was the big kind of problem that ultimately this new data science office was set up under a kind of new county assessor to try to solve using data science. So you might be thinking at first glance, okay, oh, these are the ethics folks that are coming to talk to us about bad, biased algorithms. You know what? I've heard of those before. I've read about biased discriminatory algorithms. Maybe you've heard of the Compass algorithm, used in context of recidivism. How many of you have heard of that before? Okay, a bunch of hands. Right, that's one of the paradigmatic cases. We teach it in other places. And that's often the place where our students start, even if they haven't yet taken our dedicated HCE course, Data 104. They start with, oh, the problem must be kind of like that. There must be discrimination and bias in the data, and it's getting replicated and spit back out. And this must be a problem of garbage in, garbage out. We know how to handle that. Okay, what we need to do is just go get better data, and it'll put out better results. And so you might be thinking something just like that as I introduce this. Okay, the discrimination likely is coming from something like this. But actually, that's not the case here. And the lesson is a little different. And actually, the fact that it's so different is really instructive, because to understand the differences and why you need to approach issues of fairness in model design differently depending on context show up when you contrast cases like that before. And most obvious reason why it has nothing to do, or not in the first instance, or kind of most powerfully have to do with your classic garbage in, garbage out. There's, biased data that's just getting replicated, is that if you think for a moment, and this is when we, students, we have them look at the data, they look at the various features in it, and they're thinking about, what do I see in the data? I'm seeing property characteristics, sales data. When I look through the property characteristics, a lot of them are thinking, okay, I'm looking for things that might be proxies for race, zip code, these kind of very subjective determinations of about like overall, impression or value of the property that aren't kind of fixed and quantitative. And they believe that these are places that discrimination enters in. But even if that were the case, it actually would work at cross purposes to the taxation system. Think about it for a moment. When you think about the deep historical effects, say, of redlining on devaluing the property of Black and brown homeowners, which was very much the case historically across for over a century in Cook County, what you actually get there is, well, it devalues the property. So if you find these proxies for race, you would actually find that those characteristics would undervalue the property, which would be good if you're worried about your tax burden. It would lower the tax burden. It would make it more progressive. So it's actually something much more nefarious, because while on the open market, maybe your property is lower valued because it sits in a neighborhood that's been coded as by the white public as Black and therefore risky and lower valued. On the other hand, by the tax assessment system, it's being overvalued relative to that price. So you're kind of caught, between discrimination at both ends. So it's not simply that the data has proxies for race that are being replicated and showing up. Something else is happening. And there's really two main causes to this. And they're not just technical problems. They're what we in our, we like to refer to as socio-technical issues. And to really understand what's going on, you think about the social and the technical together and at the same time. So the first one is a little bit more technical. And that has to do with the fact that simpler models, which the earlier assessor's office was using, just naturally tend to be regressive. I don't have time to go into the details about why that is. But basically below average priced homes, because their property characteristics are averaged out with homes that have higher values, they tend to regress towards the mean. And that generally leads to more overall regressive error rates. But the problem here when we think about what that actually means in practice is that if the error rate, even across the overall system, is relatively low, and even equal, say you have the same overall error rate, but in opposite directions for the lowest and highest quintile of property owners, the meaning of that error is obviously very different. The distribution of errors here is what really matters. So we take time to walk students through a little bit what these things actually mean. And we don't really formalize all of the different definitions of fairness. That's a whole other project. There's a great literature on it. That's not really at the center of this project. What we want students to start with is really just seeing what different ways that these errors, how they work out, actually affect real concrete people in the real world. What does it actually mean to be over and under assessed? This is not just an abstract problem, it's existential. There are real people that get harmed in different ways, and the same error rate for the same home, but doesn't mean the same thing. Obviously, being over versus under assessed is a big deal, but let's compare being over assessed if you're in the bottom quintile of property value versus the upper value. If you're a wealthy doctor with a very expensive home and your property is over assessed by 5%, that's an inconvenience. If you're a single mother working several jobs, making $25,000 a year and your property is over assessed by 5%, that's existential. You might lose your home. So getting students to think about this, which is not the first thing they reach for when running through and working on problems like this, just to recognize that these small regressions mean a lot for vast numbers of people in deep existential ways is part of what we try to do. Okay, that's one piece of the cause. The other is what we'd say is more properly socio-technical. One of the the other important reason for the disparity is actually a particular social process, the kind of social process that you often hear other ethicists throwing out as a solution for automated decision-making systems, putting a human in the loop. In fact, an institution that's supposed to provide accountability, that is a review board. You get assessed, you don't like your assessment, you go to a review board to contest your assessment, right? Anyone can do that, right? So it's this open-ended thing. So it's supposed to help make the process more fair. Well, as with so much when it comes to the world of formal opportunity formal equality of opportunity, it doesn't really survive the material realities of social inequality. So think about what it actually means to go before a review board and make an argument about something like this to contest your property value. It takes time, it takes resources, it takes expertise that most people don't have. So you go and you hire a tax lawyer. And it turns out that Chicago had and still does have a massive tax lawyer industry. The billboards up all over the place, basically helping the people with the means go before these review boards, contest their assessments, and therefore lower the amount that they're expected to pay. And here's some graphs that actually showed the massive disparities in who actually, the appeals rate between different income levels and the kind of the success rates of, being under versus overvalued homes. So in practice, it was actually the case that the review board was itself structurally a vector of inequality. People could rely on the expertise by paying tax experts to help them get around the system and lower their own home values. Now, you might be thinking for a moment, okay, well, great, they lowered their values. How does that really affect people who aren't able to appeal? Well, it's actually Chicago, Cook County collects a fixed amount of taxes. And how they determine how to levy it on individual homes depends on basically the overall value of property in Cook County. So if people at the upper end basically get undervalued systematically, people at the lower end, even if they're not actually overvalued, end up paying more than they would otherwise. So again, there's multiple different vectors through which a lower income and non-white communities get hit really hard by this system. Okay. So there's other dimensions of the story, but I'm turning what's an 80-minute lecture into about 20 minutes, so I'll have to skip over a few things. So the approach to this sounds probably really familiar. Use data science to fix the problem. Build a fully public, transparent, open data pipeline to make better and more accurate, more objective predictions, and use the power of those numbers basically to try to bypass this corrupt system. And this is where we got the data. They published it out on GitLab. They published their pipeline, and we asked students to basically more or less go and learn for the first time in Data 100 to build their own model and replicate this kind of process. Now, there's some powerful assumptions in here, and the final and in some ways most important part of this case study is actually about getting students to think about the assumptions about how this is supposed to work. Because so often we think, okay, you build a system where the outputs are simply more accurate, they represent reality better, that automatically translates into more fair outcomes. Now, it's precisely that assumption that we want to contest. Not only because there's multiple different definitions of fairness, different ways of assessing accuracy, as you all well know, but what fairness actually means simply can't be assessed simply in between the inputs and outputs of the model, but actually is about what happens with those outputs once they enter the real world, continuously in time and cumulatively. So we want students to learn to think about the fact that when we define, and this is, by the way, these definitions come directly from the Cook County Assessor's Office. When you see definitions of fairness as the ability of a pipeline to accurately assess, residential property values, accounting for disparities, et cetera, you're seeing an equation being drawn between accuracy and fairness. And again, that seems really intuitive to a lot of us, especially if you come out of a statistical discipline, but it's not something we should take for granted. It's something that's made to work in particular contexts. The promise of accuracy here is only meant to work because the larger socio-technical arrangement, that is all the different social institutions and different powers that are actually involved in making this whole system work. And that's why we would say fairness is a socio-technical concept. It's not portable across different algorithms. It's not something you simply point to and say, here's a way of making any algorithm more fair. It's something that's very much relative to the particular work that these things do in the world. In other words, we try to push students to move beyond the model, the simple model frame, where fairness is, restricted to a particular mathematical relationship between inputs and outputs, and rather really think about does the system work? Well, it's assumed. It's assumed that if you put these numbers out there and you show all the work behind it, that the tax lawyers will be basically too stupid. And this is what the chief data scientist actually told me when I interviewed him. They'll be too stupid to actually contest it in the review board settings. And the numbers will be so self-evidently truthful that it'll bypass this kind of circuit of inequality. Now, that's a claim, it's an assumption, comes with a lot of assumptions about how the social world works. It assumes certain things about the power of numbers and transparency, about their ability to overcome entrenched forms of expertise. And it's actually too soon to tell how well this is actually going to work in practice. But it's an assumption that isn't simply carried by the numbers themselves, but by the larger social contexts that carry it. One thing I want to point out before I close up to is when we think even about formal measures of fairness, we've black boxed them. I've referred back to the IAAO standards for measuring basically the fairness of different tax systems. If you look more closely at them, what you'll see is that they set limits to just how regressive your tax system can be. There's no assumption, they never are working with the assumption that actually maybe what's most fair is to err on the side of a more progressive taxation, that if you're going to err in any direction at all, it should be to undervalue the lower valued properties. And so if you look at in practice, even those jurisdictions that are considered to be, say, to be in accordance with the IAO standards, they're all still a bit regressive in practice, but they're considered fair because that's the sort of rely back on these established expert standards that we take for granted. Sometimes we have to open those up and question that those standards actually give us the kind of metric of fairness that actually matters in a particular context. Because again, even slightly regressive ultimately harms more than it helps. And then finally, a lot of us tend to make an equation from accuracy to fairness to justice and think that a more fair system is also more just. Well, maybe in some ways, but also really powerfully not in so many others. Fairness can function in ways to produce forms of justice, but they're not the same thing. Does this system actually make up for example, decades of accumulated overtaxation? No, it doesn't do anything for that. There's no sense of reparation or making up for the system, for a whole history of accumulated dispossessions and discriminations. So again, it's a very contingent social product, work of a kind of translation to make this hold. And maybe it will work, maybe it won't. We'll have to see. And it's crucial that our students start to see precisely how this all hangs together when they're actually going and trying to do this work. What does it really mean? How does it work? Why does it work the way it does? So just really briefly as I close up, we do this primarily in Data 100 in the form of this project, where it takes the form of 2 different Jupyter notebooks. The first one is actually kind of soft intro. They don't learn much about this background complexity. They get just introduced to the data. They learn to think context by just engaging with the data set and intuitively working through what's actually in this data without using a computer. And this was an idea that came from Andrew Bray, actually, when we started developing part of this homework with him. Don't use a computer. First, just think about the data set. What does it represent? What do you think is predictive of sale values? Draw little hand graphs just to estimate this without knowing anything about the messy background, and then gradually make the situation more and more complicated. We support this both by getting a lecture. The folks in Data 100 have been gracious enough to give me a full 80 minutes to do real justice to this case study, and just to give students that sense of, oh, the details matter. There's a lot of complexity here, and it does violence to the case if we actually cut it too short. And there's 2 discussion sections that we've created lesson plans for to help students think through this in a conversational format, which includes things just like getting them to, we have a lot of very privileged students, not everybody at Berkeley, but a lot of the students in this class are privileged. The concerns about having your home overtaxed is not something that's on their mind at all. It's not part of their reality. And it's important from our perspective to get them to step out of that, out of, often their privileged positionality, and think about what this really means for people for whom this is existential. And so we've created scenarios and budgets to help them think about, if you are somebody who lives in this kind of situation and your taxes go up by this %, what does that really mean and what do you do? To kind of make this more concrete, more real, make the stakes and impacts really come together. So I'm going to hand things off to Cathryn, Carson right now. And I'm just ending with sort of the kind of 4 big takeaways. Some of that, what I just mentioned a moment ago, practice contextual thinking and imagination, right? Really concretely, intuitively thinking about what am I really working with when I'm doing this kind of work. What I didn't tell you much about was that we use the life cycle that Lisa introduced to actually help students think through this. We walk through actually the steps that the Cook County Assessor's Office itself took in creating the pipeline, and reconstruct it by walking them through the life cycle and showing how, in addition to the more technical questions that they're taught, there's a whole set of other types of questions you need to be asking at each stage as well. We're going to do a workshop, by the way, tomorrow, where we actually get you to practice a little bit using an expanded version of the life cycle that we've created together with ADSA. I've talked a lot about these last 2, so I'm going to leave it there and thank you all and turn things over to my colleague, Cathryn Carson.
Okay. Thank you. It's such a wonderful opportunity to work concretely with data sets and models in order to bring out these larger questions of what at Berkeley we call human context and ethics. And so for the rest of this session, we're going to step back a bit and open up the range of ways in which in this program we work with students to get their heads around and their hands on human context and ethics in their data science work. This is essentially an ecosystem at Berkeley. And for us, it starts with Data 104, which is one of the main ways that students satisfy the data science major and minor requirement for human context and ethics, and also includes a dedicated course that was designed collaboratively with Victoria Robinson, whose name you've heard several times today, director of the American Cultures Program and a faculty member in ethnic studies. Then we have alongside that these interventions and engagements with other courses, integrated course content, and you have an example of that Ari just brought forward. We also have some of these larger sort of big picture teaching strategies that we've elicited out of our teaching and then tried to make available in sort of handy form, like toolkits and the life cycle that ADSA has invested so competently in. And then critical to it, though I'm not going to talk too much about it, is throughout the data science program at Berkeley, it's student teams, both working in the courses in which it's integrated and helping develop new course materials and new opportunities for students. So students encounter human context and ethics multiple times in the data science program. Ideally, it's a kind of a spiral at each stage of their learning. And these are the core areas that we'll be speaking to for the rest of this morning. There are other implementations in other parts of the program that we can discuss in the Q&A if folks are like, for instance, in the data science discovery program. So I want to start with our flagship course, Data 104. The organizing concept of Data 104, which is an upper division, usually junior or senior course, is responsible action in what we call the datafied world. What would responsible action look like in a world where data and data tools and technologies are pervasive, and you as a data science budding expert have particular capacities to work in it? What would responsible action look like it? And where do you find the leverage to take it? So Data 104 takes a kind of lead from the examples such as Cook County that we've shown you, and provides more general theoretical foundations and concepts for doing that kind of analysis. If Data 100, say, gives you a taste of what HCE looks like in data science practice, then Data 104 gives you foundations and a toolkit to use across new kinds of examples. So it's really close to this real world and tied to the practice and impacts of data science and machine learning and AI, and really explicit about ethics being tied to context and relationships between human beings in this actual world that we all live in and keep remaking. So these contexts structure the course in roughly 2-week units. You can see them here. And the way we do HCE, it's aimed at sensitizing students not only to crucial general concerns like the stakes of privacy, informed consent, fairness, transparency, those classic topics that are often central to data ethics, but also how those stakes have been settled on as the key stakes in ethical data science practice, and how, like you saw with Cook County, they're actually quite complex in real world cases, in real world action. There's no simple mapping between an idea of privacy that students may come in with, often based on their own experience walking through life with a smartphone, and the actual challenges that are at stake in transforming the world as data technologies become pervasive. So we ask ourselves, for instance, how did privacy come to be so central to data science ethics and simultaneously so fundamentally problematic in the actual world that we live in? It's not an accident that privacy is both central and completely challenged in the world that we live in. There's a historical story that brings you through how our current thinking about privacy being the #1 issue has made it impossible to resolve questions that actually operate in a world where, say, we're not defending so much against the government as companies that operate under a capitalist order. So we bring students to questions like these through these real life complexities so that when they run up against them in their own practice, they'll have experience analyzing them. Having done cases in this course, then how do you translate that to the new things that will appear 5 or 10 years from now? They'll have a generalized toolkit and a set of lenses for looking at the world. So this course, like you've seen before, fulfills the human context and ethics requirement for the major and the minor here. It's offered every semester. It's been part of the data science program since its origin. It's currently operating at 600 students a semester, so it's the 3rd largest course in the data science program. It was originally listed as a history course and then reclassified to data science along with computer science and stats classes, as John spoke about this morning. And currently it's cross-listed between data science and 2 other departments, history and STS, Science, Technology, and Society. And you could ask us, why is this a history course? We can address that in the Q&A. We're deeply persuaded that this is a model history course, bringing students to understand how they got the world that they live in and where it's going. So this is a course that's structured around reading and writing and discussion, because that's the way that we've found to get students familiarized with the foundational concepts and with practices of communication that aren't just cashed out in code. And there's a writing project that's really very action-oriented. We're a fan of real-world cases and problem-based learning. And at the same time, if you want to adequately convey foundational concepts like power and give students practice in turning them over in their minds and being ready for dialogue with others about them on other folks' terms, not just data science's own terms, then as instructors, we have to take the time and space to explore these concepts with them outside of the implementation in code. So that was Data 104. Our other dedicated course, as I've mentioned before, is Data 4AC, Data and Justice, an introduction to data science through the lens of racial justice. AC stands for the American Cultures Program, which is the one campus-wide requirement at Berkeley. And the course was designed together with the lead faculty member in that program and aims to be truly zero barrier, no previous experience, and specifically engaging for students who, through the subject matter itself, who may have not only no incoming experience, but no incoming interest or trust in coding and data. So there's a lot of focus on exploration, visualization, looking into category construction and contextualization, and the kind of multidimensional conceptual and historical work that you have to do in order to understand racial justice today. And so it starts with the communities that are most directly affected, rather than taking an analyst's position sort of above or outside. And you have some examples of capstone projects here, which are group projects that allow for peer learning and where we can make it possible community engagement, a direction where we want to go further with Victoria Robinson's help. Okay, so those are our two dedicated courses. I want to switch from the what. We gave you some integrated materials. We've talked about our dedicated courses. I want to move towards talking about the how and the sort of disciplinary and interdisciplinary foundations of what we're doing. Because what we're aiming at is to give students generalizable, structured ways of approaching these problems in the world. And that means that it's not just, I mean, some alternatives might be, pull examples from the news and let's talk about them. We've chosen not to just do that, though we often have current materials in the class because we think there's structured ways of thinking that need to be part of the discussion rather than free form, please come in with your own opinions. Second, another thing that we're not simply doing is topical coverage. We must cover privacy. We must cover IRBs. Yes, we do that, but it's in the context of providing the larger framework. Why do we have IRBs? Why are IRBs incredibly limited for handling problems of data science today with data reuse or data linkage? So it's not simply topics, it's providing this sort of structured set of ways to approach the topics that are current today and that will be current 5 years from now, but that we don't know about yet. It's getting a little bit more controversial as I go through. We're not defining a code of ethics or giving them codes of ethics to follow, though we do present, say, the ACM code of ethics, and we can't really get them to pay much attention to it. Codes of ethics are perhaps, if you have an honor code at your institution and you're dealing with ChatGPT right now, you understand that codes are not necessarily an effective way of bringing about behavioral change. So our focus is less on writing out and studying the rules and more on the practice, repeated practice of internalizing how to use analytical tools. And then the last thing is we've made a deliberate choice not to simply go through the sort of classic engineering ethics. Here are the canonical Western moral philosophical frameworks with things like the trolley problem. This is not a trolley problem kind of course. Trolley problems are so abstracted from the actual experience I could say a lot more about this from personal experience and reflection, but just say trolley problems go against the point of giving context. They step away from the human realities, and then they manufacture a thin imagined version of the moral dilemmas. We want to have students confronted in their data science education with the actual kinds of dilemmas that someone working with good intent in the Cook County Assessor's Office needs to confront in their practice. So where we pull this from, where do you get the tools and methods to do this kind of work? We take it from these areas. STS is a discipline or interdiscipline. There's a set of more classical disciplines that stand behind it. In our case, there's a pretty strong influence from history as well as other social sciences, and also just idiosyncratically for the two of us from critical theory. It's pretty high level content. It's also a pretty opinionated set of choices for how to teach data science ethics. We should be open about that. We have definite reasons for not doing, say, classical Western deontological versus utilitarian approaches. We can talk about that if you like. But much of this is typically covered in graduate classes. And like the rest of this data science curriculum, we think it's important for our undergraduates to have access to it before they go out into the world. So we're trying to take some pretty high-level conceptual stuff that's taught in these disciplines and bring it down to juniors and seniors in a technical program at scale. So that's what brings us to the why. You know that data science has a lot of power, and you want your students to be aware of that power and to use that power in ways that are responsible. Responsible including and responsible especially to others who don't have that same expertise and power that your students will have. This isn't simply a matter of having good intentions. We all know that doing good, acting rightly, can be very tricky, especially in complicated real-world contexts. So giving students ways to think about it, to reason about it with others, and make good choices under their own responsibility is what we're aiming at. And I think you are too, as instructors. You want to get your students alert to and engaged with these issues because they'll matter to their work. Their technical work is not in a vacuum. Their work can't be on autopilot. And finally, we want our students to understand that being a moral agent isn't just following a recipe. It's complicated. Good intent isn't enough. So to recap, we've given you an introduction to the core what, how, and why of human context and ethics in Berkeley's data science program. We've started with the integrated course materials from Data 100. We've stepped back to the dedicated courses and the underlying how and why. We won't have too much time today to talk about student teams and TA training, but we're happy to, that's like often a key issue. How do you get enough students who can TA a course like this in a data science program at scale? And we want to signal finally to close, as Ari teased, that we have multi-purpose teaching materials and strategies to support this work that we can share with you in the panel with the Academic Data Science Alliance on Thursday afternoon. So we'd love to hear from you. We'd like to take questions if there are any, and we're going to be around for much of the rest of the day if there's one-on-one conversations. So thank you. Question.
Do you happen to have one of those module or the Tuskegee notebook that you created for the integrated course material? Do you have one to showcase those switches?
I mean, the Data 100 materials are should all be on the Data 100 course website. So specifically that Cook County Assessor's Office, that project. If you go to data100.org.
DS100.
Yes, that's right. It's different from that domain was taken. DS100.org. And you look around for project 1A and 1B. It doesn't, I'm not sure all of the discussion materials are posted there, but some of them are. But also if you're interested, we can make the discussion available, materials available, I think with kind of the instructor notes as well. Just email us.
Yeah, question.
I was wondering, for students that are, that feel the data science is more technical exercise and are really interested in technical, like computer science, and math, and statistics, that part of it. Do you ever run into students that say, why do I need to bother learning this?
Oh, of
And
course.
if you do, then how do you handle that?
I'll give you my pat answer. It's like probability. You may not like learning probability, but if you're going to do good data science, you're going to need to learn it. In the same way with this, I don't have to persuade them because in some sense they're required, but what I want to do is draw them on the path during their time with us to say like, oh, and I learned something from this course. I don't know what it was, I can't predict what it's going to be. Is it going to be what we say about privacy, or is it going to be what we say about algorithmic bias? Maybe you have a different.
The only things I would really add to that is, we do try to think about a few different kind of categories of students in the way they, approach our class. Some who are excited about it and want to learn this kind of thing. Some who are sort of uncertain, and then a lot of them we can kind of bring over. And some who are resistant, and some of them we win over and some of them we don't. And we just kind of accept that a little bit. But I think the discussion sections with really good quality TAs makes a huge difference, because even if sort of they're like resistant to the readings and the lectures a little bit, at some level talking with their peers about these issues and in ways that are like, oh, how might this affect my life, my career? And ways that we have of talking to them about like, there's actually cynical reasons to do this. They'll make you a better data scientist. Purely cynically, if you're able to do these things better, you're able to read and write better, you'll have more like, your ability to advance, will possibilities will open up. So sometimes we give them that little bit of spiel that's like, even if you like don't actually think the ethics part matter, the context part and your ability to talk the talk will actually open up some opportunities. Yes.
So thank you for bringing this into the conversation. As a CS instructor, a lot of this is things that we have not been trained to think about or integrate into our course. So just wondering if you would point us to resources or ideas how as community college instructors, we can start to integrate and think about some of these concepts as we move to CS into this.
I would say start finding a person on your campus to talk to who finds these things interesting, because it's really hard to try to do it on your own. And when you get that personal connection that engages them, then you get the synergy of them thinking with you rather than them just serving you. Often the conventional model in this space is that you invite in a guest lecturer. We think that's better than nothing, but it really doesn't do justice to the challenges that are actually like require your involvement in co-thinking. That's one reason the Data 100 example has been so powerful for us to see that when we work together across the disciplines, that's where so much payoff comes. There are also various repositories, say under Mozilla's responsible computing or responsible computer science program. That was a big grant program that the Mozilla Foundation put forward that has the sort of classic, here are lesson plans, here are examples that you can use. And so if you Google Mozilla responsible computing, you'll find your way to various resources there too.
That's very interesting. And also just as a question, would you consider picking a case study and working with a cross-disciplinary team as a starting point from thinking about that would be useful? Is that something that you have tried?
To start with a case study and work on it. I mean, in many ways, the Cook County example was that we did some work on our own before we started collaborating with the Data 100 faculty, but it really became productive and actually worked when we sat down like with Lisa, with Andrew Bray, and really started building a homework that worked and felt integrated all the way through and fit into the course well. So yeah, that's the path forward. Yeah.
Thank you.
I'm also happy to share a syllabus for Data 104 with readings on it. We haven't made it public, but we thought about making parts of a handbook for TAs with lesson plans for how to run discussions for every week of our course. That's a bit of a work in progress, but if you reach out, I'm happy to share at least parts of it as it becomes more formalized.
Do you want us to?
Do you need
vote?
us to?
Segue. All right, you guys take one more question while I change the slides.
Yes.
I think you are reinforce for study to see the surveys to see if the course has made a difference in student.
Yeah, we do. We could probably do it more systematically. We do it in a couple different ways. We have both surveys as well as we do personal reflections in the class, like short essays. It's also part of our like larger theory to get students like thinking and reflecting about their own ethical stances and their own positionality, that like that's important pedagogically, but we also have them do a reflection at the beginning and end precisely in part to see, like get them to articulate exactly where they feel like they've come from the beginning to the end of the semester.
Awesome. Thank you so much.
Thank you.
And we have Albert Russell and Fan Wu from Tuskegee University. So really quickly, if you could come over to this side of the podium, there's like 50 people in that little thing. So if you can make sure that you can see them, you know, just like stand like slightly to that side of the podium.
Oh, no problem.
There you go.
Hi.
Okay.
We got 10 questions in the chat already. We haven't even started.
Right. Oops, let me get rid of this thing. Okay. You're on.
I'm gonna go back to here. Well, good morning, everyone. I would be the person standing between you and lunch, so I'll try to be brief. I normally don't announce that I'm a pastor, but this is a moment where I have to announce that because usually I'm the person standing between the congregation and them going home to eat. So we'll be brief today. I do want to say thank you to everyone here. I'm grateful to be here. It's been a marvelous time just soaking everything up. I'm Albert Russell. I am the Associate Professor of Chemistry at Tuskegee, and I'm also the Assistant Provost for Student Matters and Academic Programs. And Dr. Wu, you want to introduce yourself?
Yes. Good morning, everyone. And my name is Fan Wu, and I'm a professor of the Computer Science Department, and I'm also the department chair, department head of the Computer Science.
All right, so we're going to jump right in. And to be blunt up front, we are in the process of developing or submitting for approval a data science BS degree, right? We have many data science initiatives at Tuskegee, but we don't have a data science degree program. And so Dr. Wu, myself, Dr. Carter, and several other deans and faculty members, we all, and Dr. Kwanzaa, I'm sorry, I see you back there. We came together to ensure that we could put this degree program together, that it would, and make sure that it was robust, make sure it touched the areas it needed to touch, and also to make sure that it wasn't purely theoretical. I think we made that decision early on in the development that this wouldn't be a purely theoretical program, just to ensure that it touched the maximum amount of people. So the reason I put this slide in is because on yesterday, I was talking to a colleague who had no idea what Tuskegee was. At first, I'm like, I'll just talk about the program and the classes. But that gave me pause because I started thinking, wow, maybe there's someone else who has no idea where Tuskegee is or what Tuskegee is. So Tuskegee is a small private HBCU in Alabama, about 30 miles north of Montgomery. How many of you have heard of Montgomery? Okay, great. Give yourself a round of applause. All right. It was founded initially near a church in Tuskegee called Butler Chapel AME Church. It was the idea of Lewis Adams, who was a local educator, who came together with a white banker. And in exchange for the black vote in Macon County, they were able to get a resolution passed to actually start Tuskegee Normal School or Tuskegee Institute Normal School. It wasn't Tuskegee University at the time. It started with about 30 students on the 4th of July in 1881. The permanent site came from an abandoned plantation. And that tells you a lot about the university and its inception, the fact that it was started only 15 years after emancipation, right? And a lot of people tend to question the need for HBCUs as if HBCUs just popped up out of nowhere. No, HBCUs were founded simply because we couldn't go anywhere else to get an education. And it's that simple, right? There's no, we don't need a data analytics study to understand that part, right? I mean, it is what it is. We had to have institutions of higher learning. We were not welcome at other institutions of higher learning, so we started our own. The main goal of Tuskegee was not to produce farmers or tradesmen, even though it's in the country. And there's a lot of farmland and people grew all types of different crops. I know everyone here has heard of George Washington Carver. Yes, raise it. Give yourselves another round of applause. Right. So Dr. Carver was instrumental in the history of the university because Dr. Carver, after being lured to Tuskegee by Booker T. Washington, who I'll talk about in a second, he revolutionized the way farmers in the area farm their crops. What he did was taught them to plant crops like peanuts and sweet potatoes that enriched the soil rather than depleting the soil. So farmers didn't have to like basically trash the land after several years and start from scratch. And so Carver was instrumental. I don't want to talk I can give the whole presentation about Carver and Booker T. Washington, but we're going to talk about data science. So if you ever been to come to the campus, you'll see that there are several buildings on campus that have handmade bricks, because one of the foci of study for the students at the original institute was basically being tradesmen. So many of the buildings have handmade, hand-fired bricks. And if you come to campus, all the buildings look really old. That's on purpose because we are a national historical site. So a lot of times when you think about renovation, what happens is they go in and gut the building, but keep the exterior because those bricks, a lot of those bricks were made by hand. So let me move on here. This is, and I'm just kind of giving you a little bit of a progression. This is the first building that was erected on campus. This is a digitized version of this building. We have an excellent architecture program, by the way, and design program. Just wanted to throw that in there because I think Dr. Daniels is the person who actually is responsible for this digitization. But this is the first building that was erected on campus in 1883. And it was funded by Alfred H. Porter. If you come on campus, you will see this is where everyone goes to take their photo before they leave. This is a monument of Booker T. Washington. And you can see he's lifting a veil or cover from the eyes of this crouched down person who in the statue is depicted as a former slave. And the title of this monument is Lifting the Veil of Ignorance. So this is really what Tuskegee was all about. This is what Booker T. Washington, whose mantra was to train the head, the hand, and the heart. And we still do that. And that's why we made an early decision not to make this data science program overly theoretical, but also make it practical. And you can see from even the last presentation that practicality actually matters, right? So, and then this is currently, this is the student union / bookstore. And this is also where our financial aid and admissions offices are located. But this is Margaret Murray Washington Hall, named after one of Booker T. Washington's wives. And this is what you'll see when you first come to campus, as soon as you come into the gate. So I kind of wanted to show that progression because I want to talk about where we are right now. Right, I already talked about the location. We have our enrollment is about 2,700 students. The goal is about 3,000, but after COVID, enrollment dipped and enrollment has been really declining for the last 5 years. So we have a new provost who's kind of dedicated to increasing enrollment. We have 8 colleges and schools. I won't name them all, And we have over 35 BS programs. We have master's programs in public health and several other disciplines. We have PhD programs in material science and engineering, integrated biosciences, and that program has produced over 100 PhDs up to date. We have integrated public policy and development and interdisciplinary pathobiology. Those are our PhD programs. We also have a DVM program that produces 75% of all African-American veterinarians in the United States. And we have several research, both sides, but the main ones I have listed here. You have people doing research in all types of different things, but the main one I have listed here, we do a lot of breast and prostate cancer research, and that's because those two diseases are linked to several different layers of health disparities that mainly occur in African-American populations. Dr. Carter has been instrumental in working with that program and working underneath the U54 grant that supports that. We do a lot of studies in health disparities. We do a lot of material science and engineering, and we do bioethics. I don't know if you all remember the Clinton apology for the syphilis experiment, but one of the things that came out of that was was the renovation of a building that used to be a hospital on campus, and now it's the Tuskegee University Center for Bioethics. And so that's just a little bit about the current composition. The question is why data science and why now? And I'll be honest with you, I'm not a data scientist. I'm a chemist by training. I'm not a data scientist, but when the market presents a specific demand, you have two choices. You can respond to it or you can stand pat. And so we wanted to respond to the demands of the market because data science is the thing now. But this came from a book written by two authors from MIT. It's the Essential Data Science, like a primer. And one of the things that they say is this, that data science is not autonomous, right? Data science requires that somebody who's well-skilled and well-trained have some oversight over the different stages of the process that occur in data science, right? So it's not just tapping a button and walking out of the room. You need human interaction in order to clean data, separate data, analyze data, and then develop these visualizations. So with that being said, how do you develop a cohort of data scientists? You have to have programs like the one here at Berkeley, like the data science programs at your various institutions. If you have them, that train people. And so we're responding to this need. And I have here just some infographics. And I have the date circled here, May 13, 2017. This was an article in Forbes. And here it says by 2020, I don't know if everybody can see this, but it says by 2020, and this was in 2017, the number of jobs for all U.S. data professionals will increase by 364,000 openings to 2,720,000 according to IBM. So this is, again, one of the areas where you see rapid growth and you see rapid development. I have another infographic here, which is a graph just to illustrate one of the main reasons why we feel that we need a data science program at Tuskegee. And that is within the data science workforce, only 4.2% of those who are in that workforce are African-American, right? And so this is a really critical thing when you think about the absence of African-Americans in STEM, right? This is critical to also bring in this piece and kind of use that as a driver to push us forward in the development of this data science program. I have here also some statistics from the Bureau of Labor and Statistics, updated on May 1st. The median annual wage, which is what every student that I know wants to know, right? How much am I going to make? This is the median wage, $100,000, a little bit over $100,000. The job outlook, that the area of data science is projected to grow from by 36% between the years, and this is updated in May 2023, but this was a projection for 2021 to 2031. And according to the Bureau of Labor and Statistics, this is a faster than average growth rate compared to other occupations. And so why now, right? There are 486 data science degree programs according to the data that I could find, and that was posted or last updated in 2019. I'm sure there are more now. 259 schools, 201 master's programs, 102 certificate programs, 46 BS programs, 20 PhD programs, 7 associate's degree programs, but 0 at an HBCU, right? There are several HBCUs that may have data science initiatives. There is no pure Bachelor of Science degree in data science at an HBCU currently that we know of. So Tuskegee is poised to be the first and only HBCU to offer a BS program in data science. And again, this is a response to a need. When you see, how many of you remember the movie Robots? Anybody? It's one of my favorite movies. Anybody? Come on, you. Okay. Don't be ashamed. I've watched it 1,000 times. When it came out, my kids were in elementary school, and I loved the movie. Right, it had a great theme. But one of the things that Big Will would say: you see a need, you feel a need. Exactly. So that's part of our impetus. So the purpose and the goal of our program, again, is training and giving students those technical skills that are necessary to work in a career in the discipline of data science, and also focus on the knowledge and skills required to meet government and industry standards, right? This is a need that will not go away. So again, you have two choices. You can respond to it or you can stand pat, right? So I want to talk a little bit. How much time do I have? My sermons don't go this long, by the way. But these 4 pillars: domain knowledge, math and statistics skills, computer science, communication and visualization. We wanted to ensure that what we offer to our students in this program that we've submitted for approval touches these 4 pillars, right? So one of the things about this program and one of the beauties of it is that it's interdisciplinary, right? We initially started out with 5 colleges or 5 academic units trying to come together to put this program to develop it. But, doing this type of work is difficult, it's time consuming, and some people who came to the table left the table. So the people who were left at the table, we just did the work. So the College of Arts and Sciences is one of the players. The College of Business and Information Sciences is another player. And then Canes, which is our College of Agriculture, Environment, and Natural Sciences, that's the other piece. When we haven't excluded any academic units, but these were the major academic units that helped to put the curriculum together. We want to make sure that when we offer this program, that the skills necessary for each one of these pillars are covered, right? And the reason why it's important for it to be interdisciplinary is because, as all of us know, this is a new field, right? Relatively new. Well, a new name. Data science, we've been doing it for a long time, but now it's packaged up with a nice bow on it and a label on the box. But we have within all these academic units, we have different pockets of people who've been doing data science all along. So now we just are bringing them together, for a cause that is going to be beneficial to each unit. We already have multiple faculty doing this. And then one of the key functions or the key highlights of our program is this ethics piece in data science. Particularly, that was highlighted in that last presentation. And so we have Dr. Carter in the behavior and social sciences track, which I'm going to show you in a second, who will be instrumental in helping us to ensure that the ethics in data science and the human component of data science is not only highlighted, but is prioritized. My information. So this is what happens. I don't have a Mac, I have a PC. This had words in it, but that's okay. No, I didn't have any animation. That's okay. So, and again, I don't remember what each one of these things is. I'm just going to be honest, but this was taken from a book by Keller and Tierney, and it just talked about the different skill sets that data scientists need to have. And I do have this. If anybody's interested, I'll be happy to send it to you. But the centerpiece is data science, and all of these with different skill sets. And I can't, right now, I'm drawing a blank. But the point is that the skill sets are going to be addressed within our different academic units. So I have here like kind of an overview of what the major entails. So it's in the major is 36 credits, and those credits are spread out between CAS, Canes, and CBiz. And then you can see here around this diagram, there are different tracks. So we have a agriculture track because we do a lot of GIS work in agriculture. So we have an agriculture track, which is 18 credits. We have a social sciences track, which is 18 credits. And then we have a business and computer science track, which is also 18 credits. So we want the degree to be very flexible. We have our core requirements, which is what every incoming freshman will have to take. And I have here 36 credits. It's actually broken down further, but I don't want to break that out into details. But there are a total of 36 credits in that university core, and then 34 credits of electives, 27 of which are actual electives, and then 7 of which are free electives. So the degree itself total is 124 credits. You can't read this unless you have Steve Austin bionic eyes, but I just wanted to put this up here to show like the breakout of the different tracks, and also to show how we structured this major in the sense of what the major credit courses are, what the additional requirements are, because we did begrudgingly have to put in a little bit of higher level math like Cal 1 and linear algebra. We wanted to make sure that students had that training before they got into the computer science courses and the other courses. They may require some knowledge of those areas, so some prior knowledge. So again, I have this. If anybody's interested, I'll be happy to send it to you. These are program learning outcomes. So these are generalized learning outcomes from this program. And the way we developed these was to align them with our university mission, right? So I'm not going to go through, I'm taking liberty there because I've heard several people say, I'm not going to read all this. So I'm not going to read all of this to you. However, we do want to stress critical thinking, communicating of data science concepts, problem analysis, and problem solving using data science techniques. We want to stress teamwork and collaboration. Again, this is a multidisciplinary degree program. And so even that is a way for us to practice what we're preaching by stressing teamwork and collaboration, development of new ideas related to data science, and then interdisciplinary content comprehension. So how do students learn data science and how data science applies across different domains? What will make us remarkable, right? It doesn't make sense to have a program or degree program if there's not something about that program that causes you to stand out. So again, I'll stress it and I'll say it again and again and again. We're the first and only HBCU at this point to offer a BS degree in data science. We also want to stress ethics and not just data science, but also touch other areas like artificial intelligence and machine learning. And the reason why ethics is such a big focus at Tuskegee, how many of you, I know y'all getting tired of me asking that, that's the preacher in me. How many of you have heard about the syphilis experiment, the Tuskegee, exactly. How many of you have heard of Henrietta Lacks? Anybody? Okay, so all of she was a central figure. Tuskegee mass produced her cells for polio vaccine research, right? And with the syphilis experiment, we all understand the ethical implications of that. And so we have this kind of niche area where we can be very effective in stressing how ethics relates to data science, and also how ethics relates to like how we move about in the world. So we want to make sure that that's one of the major foci of our program, is teaching students, again, the ethical implications of data science and data science in practice. We want to leverage our current health disparities research. There's tons of data within that research that we can use as training and teaching tools, increase the mobility of African Americans in this new field. Again, I showed you that number, 4.2%, and not just African Americans, but all minorities. We want flexible degree options. And the reason why I say that is because maybe you have a student who does not want to do the full social sciences track. Maybe they want to mix social sciences with ag and computer science and business. So we want to make sure that we have, and one of the things that I've been most impressed by here is how flexible everything is. I mean, it's a very flexible system that allows students to operate at their maximum potential by doing what they love, right? Or not just being stagnant and stuck in a box, but being able to touch different areas. And that's important because if your students in your program, if you have them, operating in a certain capacity, those students are going to be also your number one recruiting tool. Thank you. I'll go back to that. I only got like 30 seconds left, but I will go back to that. And we also, I want to thank Berkeley for the support. We all actually got a support letter to put with our package to our accrediting body from UC Berkeley. So thank you for that. But we also have other partners, IBM, Case Western, and IBM and Case Western actually have courses that our students will be able to take as elective courses. And so we have a lot of buy-in from our partners. Let's see. This is money. I'm an administrator, so we got to talk dollars and cents. So in year one, we're projecting 15 majors, and this is not pulling people from other majors. These are new majors that we're projecting. And we're projected also to take a hit there. The program cost includes salary for 2 new faculty and then other program operating costs. So year two, 25 learners. So the goal is to increase the number of majors by 10 in year two. And you can see that there's a positive financial benefit there. And from year 2 through year 5, we're looking at our totals after 5 years of this program being in existence. What we project is a $2.7 million revenue increase based on this particular program. Let me see what else I have. Okay, yeah, we're almost done. 30 seconds, 35 seconds. So challenges and opportunities. Obviously, the challenge is hiring faculty, right? And in an area like this where faculty can command a very high salary, and at a small institution that really tries to squeeze blood out of a turnip at every chance we get, that's going to be a challenge, but I don't think it's going to be an insurmountable challenge. We also have, again, as an opportunity, repurpose some of our faculty who are already engaged in data science type work, maintaining it, that should have been another bullet, but maintaining our digital infrastructure. I was blown away just by the speed of the server when we logged in to do the demos on the Jupyter notebooks. I was blown away by that. So we need to make sure that we have the digital infrastructure in place so that we can make this program high quality. And then developing this culture of data analytics on campus and using the students in the program, around campus in areas where data analytics is very important. We have an office of institutional effectiveness, and I'm not knocking that office, but I think we can improve that office and have that office also as kind of like an internship site for students who wish to do so that are in this program. And we want to be a flagship university for this data science degree. And I've already talked about physical infrastructure and digital infrastructure, and then also repurpose some physical spaces to be our data science laboratories and things like that, data analytics laboratories and things like that. Do I really want to do this, right?
You want to do it?
Okay, let's go back. Give me 10 seconds.
Yes.
This is the blank slide. From left to right, I'm just gonna, is this touchscreen? No?
No.
Great. All right, so we have data visualization, stats and probability, machine learning, communication, domain expertise, let's see, data ethics and regulation, data wrangling and databases, and then computer science and high power computing. So these are not necessarily skills that every data scientist, thank you, by the way. I've been admiring your red backlit keyboard all day, by the way. These are not, a data science doesn't have to have every single one of those competencies, but it's important for them to have a little bit of each in order to be effective. So with that being said, it's 12:02, and I think I'm 1 minute over time. So I'll stop here and open the floor for questions. Oh, let me thank our team too. Dr. Carter, who's here with us, Dr. Wu, who's also here with us, Dr. Yasmin, who's also very intricately involved with the program here at Berkeley, Dr. Yademchi, Dr. Ndoye, who's also involved here at Berkeley, Dr. Nori, who was our online director for several years. He was also instrumental in helping us put the initial pieces of this program together. Dr. Kwanzaa, who's also here, he moved up actually. Dr. Kwanzaa, and then the deans of business, arts and sciences and agriculture, Dr. Kuhn, Dr. Prakash, and Dr. Bolden Tiller. So with that being said, I'll stop and open the floor for questions. Go ahead.
But to reflect, a lot of curriculum
Mhm.
for data science are missing the voices of African American intellectual, spiritual, and their voices. You gonna form a team to look at the curriculum and bring those voices and empower them in the curriculum.
I think, Dr. Carter, you want to speak to that? I think that is an underlying focus of our degree program. And I think that, you know, again, with the social science, social and behavioral science aspect of the program, we're going to use that as a platform to do exactly what you just said. Go ahead, Dr. Carter.
One of the things we've been working on here in this collaboration with Berkeley is that data 6 course that actually looks at a lot of the issues. Now, in the course that we have developed, okay, the primary focus will be on not only looking at the data, but also creating different things, sets, different algorithms, so that we make it more inclusive.
Great question. Oh,
One last-
go ahead, and then.
So last year, when your team came and presented us, you had a group of students.
Mhm.
In Berkeley, they took a couple courses. Are they, what happened? Did they go back or are they?
They're here now, right? They're here. Well, there's a new cohort, but they're on campus now.
Did
For-
Berkeley send also a team of students to Tuskegee?
I'm not sure about that.
Yes.
Go ahead.
So what happened last year is the students went for 8 weeks. Some of them took the basic course that we're trying to put the tool a bit. Two others were data 8. And then when they went back, we supported Dr. Yowski, who taught data 8 for the first time on the campus, and the two students who were taking data 8 in the summer acted as the student TAs for the course. She then taught it again in the spring semester. And then this summer, we've got a new batch of Tuskegee students, some taking data 6 and data 8 as well as we have a research discovery pedagogy course that's overlaid where all the students take and they get an exposure to different kinds of data with a little bit of research around learning about a topic and doing answers. And we're looking forward to continuing that.
Go ahead, Dr. Quanz.
I just wanted to add to the presentation that Russell has made. He kept on saying that some of this work is already going on in different departments. And I wanted to give an example of what our college has been doing in the last 10 years. That was when big data was the big thing. For instance, we our center, the Educated Climate Change Center, and I have about 4 or 5 other colleagues. We went intensive in big data. We work with satellite data, climate modeling, environmental modeling, and all these things. And we had good collaboration with the National Geospatial Intelligence Agency, for instance, which is one branch of the ICE. And we had how at the point we had probably somewhere $2,000 grant, and all our students, NGA will come to campus every time. Talking about the curriculum, NGA has the geospatial defined curriculum for different universities, and we had to incorporate that into all our courses, remote sensing, GIS, machine learning, and all those stuff. And most of our graduate students will go to NGA during the summer to do internships. They'll go through 6 months of security clearance, and once they get it, they will go back in spring or any other time. And almost 80 to 90% of our students are highly employed, NGA, or some of the secret service and all that. This has been going on. We have a project called digital agriculture, for instance, where we are introducing, we do a 2-week model, just introduce students to Python programming. And students who get interested, the following semester, they do a full semester into Python programming, which has Dr. Farouk teaches 2 weeks for me. We have, I teach, for instance, machine learning, image processing. I have my colleague, Dr. Paul, who teaches Python, GIS, and things like that. So some of this work is going on, and I just wanted to add that this particular new program brings all the different departments together. I wanted to demonstrate how it's going on, and our students have actively been part of it. And I remember that probably 6 or 7 years ago, when our students would go to NGA during the summer, when they came back, their first issue was data science. And so what we do, we asked them to go to College of Agriculture to go and take some computer science courses. So I think this is great, and this is my first time of coming here, and I'm excited about it.
Yeah, so
Oh, go ahead, I'll go right here.
Just want to add some background information. So in computer science department, Tuskegee, actually, we launched a master program in data science in spring 2021. So with the support from the National Science Foundation. And we actually developed a series of data science courses in graduate level. And we also developed several undergraduate level data science courses. So now we can have a opportunity to extend this to the BS program in data science. That is really exciting.
Yeah.
So
I had a question right here. Go ahead.
It's kind of a two-part question, and it's basically, first, where do your STEM students go for their professional careers? And like both geographically and kind of in terms of what they want to do, and how do you see your data science graduates, like where would they go? Where do you think they will find?
That's a good question.
Other places locally, other places in the area, or is there industry, like are there specific like hubs that you're planning for them to?
That's a good question.
Find employments?
Well, I think to speak to the first part of your question, our students they go everywhere. We have students. Our alumni network is top tier as far as students across the country working in industry, working in academia, working in different fields. So we have students everywhere. So I don't think that there's going to be any change or any movement away from that model with this data science program. We have several industry contacts and several industry connections. They come to campus, not just on career day or career fair, but they come all the time and they seek our students out. And so I don't see this being any different. I think the data science program, once it's up and running and once we generate that first cohort of graduates, those students are going to be in very high demand all over the country.
yeah, and we also have some graduate students, they work for the federal agency, and they are doing like a data science related work. And we got very good feedback, and they come back to us, hey, do you have any graduate data science? So yeah, we also have a very good relationship with cooperations with the federal agencies.
Yes.
And if I could add quickly, like you said, federal agencies, the National Geospatial Intelligence Agency is coming to campus every time to recruit. The issue in the US, no one. All these are federal agencies are coming out, and they are really excelling. They are doing well.